Currently associated with Intel Technology, Bangalore. He has a 15 plus years of experience in digital ASIC and FPGA design. He has delivered more than 100 corporate trainings. He has completed his master's in VLSI design from Anna University, Chennai, and BE in Triple E from GCT Coimbatore. So I'll just introduce a small, is a brief biodata because he's having a lot of credentials towards this technology, so that he will be sharing with you all experience and knowledge. So yeah, our secretary sir is there online, Dr. SG Prasad sir is our honorary secretary of IT Bangalore. I'll request him to speak few words, sir, before we start this training.
Yeah, thank you. Yeah, very good morning to one and all joined today. So about IIT Bangalore, it's as you all aware, IIT is one of the leading professional society, and it has got almost more than 60 centers across the country. And IIT Bangalore specifically, it has been very vibrant, and we are trying to ensure to provide the maximum qualities for all our stakeholders, like for the engineers from industries, or it could be for the academia, students. I mean, a lot of programs we have been doing. So this is one such, short-term training program, and we are very fortunate to have Mr. Padmanabhan. So he happens to be my earlier colleague, and he has got a very good experience, as already was been briefly explained his profile. He has got a very rich experience in trainings in various industries. For various industries, he has given, and very good expertise, I can say, on the domain. And this time, we are very fortunate that he has agreed and joined the IIT Bangalore to share his expertise. I request all the participants to kindly, inform your other colleagues also to join this thing and get the maximum benefit of it. And please, we try to make it interactive. Of course, I think the course faculty will tell you, so that the course, whatever we are putting the efforts, it can be rightly utilized. So with that brief, I wish you all the best, and I wish you success for this particular program. Yeah.
Yeah, thank you, sir.
Yes, sir. Thank you very much, sir. Thank you very much, Prasad, sir. So shall I go ahead and share the screen, sir?
Yes, sir. Yes, sir. Please, sir.
So can you please confirm, is it visible, sir?
It's visible, sir. It's coming, sir, on the screen, sir.
All right. Yeah. Fine, sir. Thank you very much for the confirmation. So good morning, everyone. Welcome to the advanced FPGA design course using Intel FPGAs. I'll just give a quick idea of like what would be the course topics, what we are going to learn in this specific course, so that you'll get a fair idea like what would be the coverage and how are we going to perform simulation, synthesis, and then the filter operation, implementing the design onto the board, timing, closure, everything. So I'll just give a brief introduction. So first we are going to start with what is an FPGA. Today I'm going to introduce you to that, and then introduction to Intel FPGAs. You all knew that Altera has been acquired by Intel in 2016, and we call this as Intel FPGAs. So then what are the applications? And then we have a Quartus Prime design software tool flow. So what is available to that? And how are we going to perform simulation? And we do synthesis and filter operations. We are going to learn about the HDL coding techniques, which are the proper HDL coding techniques. How are we going to optimize the code? Right, all those things. And then we implement the design onto the board. What are the different implementation options, everything. Then later we are going to learn about the timing analysis. What is the concept of timing analysis? What is a static timing analysis? And how are we going to apply timing constraints to the design? Right, for example, it's a pure combinational logic block. How are we going to apply the timing constraints? If it is a sequential logic block, like how do we apply create clock and then set input delay, set output delay? And how do we apply timing exceptions like false paths, multi-cycle paths, etc.? And when the design is not meeting timing, what are the different various options we have? For example, you can see here that is explained here as a timing closure. That means we are going to ensure that the design is not having any setup or hold violations, all those things. And this is on the block level, right? And then we are going to create a system where we need to understand what is the intellectual property, what is an IP core, right? And then we are going to use IP cores and then we create a system. So IP core based, right, system design. So we create, right, that IP core based system on chip design where we need to use the platform designer and then we need to use system integration. And then we are also going to generate an embedded system using the NIAS2 soft core processor, which is available. So when you say soft core processor, it is going to use the resources which are present inside the FPGA. Followed by that, we have multiple design examples that we are going to do. We are going to use the Max10 device, which is the D10 light board. Using that, we can have a proper hands-on also. So these are the different topics that has been planned. Each and every topics will have a subtopic, which we need to get into the details, and then we are going to have detailed session on all these topics. If you have any questions, you can stop me. We can have discussion and then we can move forward. There is nothing wrong in it. The idea is to ensure that everybody should have the idea of what is the coverage and how are we going to learn it and what is the complete session, right? The coverage details. So let us start with what is an FPGA. We all knew that the FPGA stands for a field programmable gate array. That's what we call that as an FPGA. Right. So now let us split that into parts and understand what is this field programmable gate array. What is the meaning of the word programmable? Why do we call that as gate array? All those information. So let us explore and understand that in detail. So an FPGA is a set of Lego bricks made to any design of choice. So we all knew that it is a programmable chip. That means it is a reconfigurable chip. It is a reprogrammable or a reconfigurable chip. That's what we say. So what is the specific logic we can say? It is a set of Lego bricks made to any design of choice, we can say. Right. Now let us move on to the next step. Now what is this? The expansion of the field programmable gate array. That means we can see that gates refers to the transistors. Now we can say that these are the tiny pieces of hardware on a chip that make up the design. That means you can see that multi-million gate level design, like that we will say. That means it has different number of gates that are present inside. And what is the meaning of the word array? When we say array means there are many of them manufactured on the same chip. That means they are multi-billion. That's what we'll say, that billion gate level design. So we can see that when you say gate, that means these are the tiny pieces of hardware, like in which we say, right? And then when you say array, that means it is not only single gate. There are billion gates that are available inside the chip. And when you say field programmable, what is the meaning of that? When you say the connections between the internal components are programmable after deployment. The meaning is like, since it is reconfigurable and it is reprogrammable, now we can check the functionality of a counter. After some time, you can check the functionality of an FAR filter. Like that, we can check for multiple informations. So that means FPGA is nothing but which is a programmable hardware. That's what is the expansion we say. Now the field programmable gate array ensures that it is having a set of gates. That means these are the tiny pieces of hardware and they are not, right, only small. That means they will have millions. They are arranged into the larger structures. And it clearly shows that the field programmable means the connection between the internal components are programmable after deployment. That's the basic scenario which we came across. Right. Now, what is the basic information, right? When we learn something about a concept, right? The first question is we will ask why, right? So why do we need to learn this FPGA? Second, then only we can say that how do we program that and what are the things, right? Now we need to understand that what are the components that are present inside the FPGA. Now we have understood what is an FPGA, but what is present inside that FPGA, that we need to understand. So I'm going to spend some time in showing you that what are the components that are present inside the FPGA. That will help us to understand how are we going to use those resources which are present inside the FPGA based on our HDL coding. Like we are going to write either VHDL or Verilog or system Verilog, any HDL, and then we are going to program. So how are we going to do that? How your code is going to use those resources? Let us spend some time in that. Now, how an FPGA become and what you want it to be? If you see here, the FPGA is made up of small building blocks of logic and other functions. So the FPGA is made up of small building blocks of logic and other functions. When you say, in this case, we have to be very clear that building blocks of logic and other functions. So building blocks of logic means it can be combinational logic. It can also be sequential logic. That means you are going to program a kind of gate, or you are going to write code for decoder, encoder, etc. We are also going to write code for memory, finite state machines, etc. Right? So it will have the different set of building blocks of logic and then other functions. That means on the right hand side you can see different square blocks of different colors. That means you could see that there are multiple resources that are present inside an FPGA, and based on our coding, right, it is going to use those resources effectively to perform a specific digital function. That's a basic idea. Right. Now, what is very important for us is how are we going to get those resources, and how are we going to connect them, and how are we going to configure them to use it for a specific function. That's what we need to understand. To get into that, there are three important C's that are available inside the FPGA. Now, the first thing is the building blocks you choose. Okay. That means you need to choose the components. You need to choose the components means there are multiple components that are available in your FPGA, but based on your HDL coding, it is going to choose something. That means there are three important C's. The first C is called as choose. The second C is called as configure. Right? How do you configure them? And the third C is called as connect. That means how are we going to connect them? So what is important for us is we are going to understand that the building blocks you choose, how you configure them, and how you connect them. Okay, if you know how to choose these components, and we know that how do we configure these components. For example, whether you wanted a RAM, a single port RAM or a dual port RAM, or a single port ROM or a dual port ROM. You need to configure those components, right? And then finally, you need to make connection between those components. That's what we say, that how do you connect them, right? So when we know how to choose the components, and we know how to configure the components, and if you know how to connect the components, then that will determine what the function the FPGA performs. So what is the basic logic? What is the key takeaway here? We have understood what is the definition of the field programmable gate array, and how do you ensure that the FPGA becomes, right? The FPGA becomes based on the set of three important C's. One is we should know how to choose the components. The second thing, we should know how to configure them. And third, we should know how to connect them. So by performing these three, we will come to know what function the FPGA performs. You will come to know whether it is working like a pure combinational logic like encoder, decoder, etc., or it is working like a counter or shift register or finite state machine or memory, etc. That we will come to know, right? We will also come to know that it is working like a processor or a digital signal processing application, anything, right? Right. Now, what is the important information which we need to look into is what are the components that are present inside the FPGA. I showed you as boxes, right, in the earlier slide. But what are those boxes? What are the different set of components? Let us explore that now. The first basic building block, right, is called as the lookup table, which is called as a LUT. So what is available inside the FPGA is the lookup table, okay, which is called as the LUT. That's what we call. So what is this lookup table? Let us understand that in detail now. Okay. Now, when we need to know what is this lookup table, you can get a clear picture by going through this slide. You can see that the lookup table is the foundation, right? And this shows a 4-input lookup table, which is designed by two 3-input lookup tables and a 2:1 multiplexer. So now we can see that Y is equal to, right, A bar, B, then C bar, then D. Like that you can connect it now. So for example, if it is a 2-input lookup table, then what will have when you say then 2 power 2, then you can go for 4 possible combinations. That means 0, 0, 0, 1, 1, 0, 1, 1, like that. If it is a 4-input lookup table, then we can go for 2 power 4, which is called as 16 possible combinations. So what is the basic component that is present inside the FPGA when you call that as the lookup table? That's what we call that as a LUT. Right. So now with the LUT itself, we can perform everything when you say that is not possible, right? That's what we are going to understand. What is the other component, right? Where this lookup table will sit. That's what we need to understand. So first we have understood what is the lookup table. That means what is the basic component and where this basic component is going to be residing inside the FPGA chip. Now we will get a bigger picture, slightly bigger picture. Now the slightly bigger picture is called as adaptive logic module, which is called as ALM. Okay, let me explain that to you in a clear manner. Now in the earlier slide, we have gone through the lookup table, which is called as the LUT, right? Now, what is the basic scenario here if you say? Now, for example, this is having an 8-input lookup table. 8-input lookup table means you can understand 2 power 8 combinations. So in the earlier low-end FPGAs, you will have, right, a 4-input lookup table. Right now you can see that you have an 8-input lookup table. And why it is called as fracturable? That means it need not to be always 8 input. It can be broken down into 2 4 inputs or 5 3 or 6 2 or 7 1 in whatever way you want it. That's what we call this as a fracturable lookup table, so that you can break that into pieces. So now you can see that an adaptive logic module is one which has, right, 8-input lookup table and 2 3-input adders and then 2 registers. Now you can get a clear idea. For a combinational logic, I want a lookup table. Then the output of that can be connected to a register. So that means you can see that, okay, for modeling your matches, flip-flops, right? The idea of a counter, you need some register. So the adaptive logic module ALM has 8-input lookup table, 2 3-input adders, and then 2 registers. Now, why are these things important? Because these things will help us to model our design. So whatever code you write, then we need to ensure that the code is going to take that specific functionality. We can get a clear picture. Okay. So now what is the basic thought process? First, we should know what is a lookup table, LUT. Second thing, what we should know is called as the ALM, which is called as the adaptive logic module. So an adaptive logic module is one which has the 8-input fracturable lookup table, 2 3-input adders, and then 2 registers. That's all. Okay, now first we have drawn a simple square box, which is a lookup table. Yes.
I have one note. This adder has 2 input, right?
2 3-input adders means, like you can see that like a multiplexer, right? You can take this combination and based on that, this will be connected to this.
Okay, but I'm able to see only 2 input that adder has. One is from left side and from the top side.
Correct. That adders will be taken based on the sum and carry, right? That through the mux that will be taken to the register.
Okay, but it is a 2 input, right?
Right.
2 input and 2 output.
Right. So that output with whatever you get, right? For example, when you add 2 numbers, you will be getting a sum and a carry, right? So based on that it will decide based on the multiplexer, which will be taken to the register. Is that clear to you?
Yes, sir. Yes.
Yeah. So now the first box is called as the lookup table.
Hello, sir.
Right? Because you may have a carry in for an adder also, right? Yeah. Tell me.
Hello.
Yes.
Yes, sir. This adaptive logic module, this combo is present in single logic table or what, sir?
Right. So this adaptive logic module, whenever we have, right? So it has an 8-input lookup table inside this itself. Okay. So now that means you can go up to 2 power 8, but in all the combinations, you may not require 2 power 8, right? Because when we write a Boolean equation, you may not require a 8-input lookup table. Sometimes what will happen, we wanted to break that into 2 4 input or 5 input or 3 input or 6 input or 2 input, right? In that case, this lookup table can be broken down into pieces. That's what they say, call that as a fracturable lookup table.
Okay, sir.
Okay, so I will just show that in next slide. You can just get some idea. Maybe you may get in clear detail here. For example, I can break this adaptive lookup table into 3 and 5, or it can be broken down into 7 and 1, or it can be broken down into 2, 4. Are you able to get the idea of picture here?
Yes, sir.
Right? Any other doubt you have?
No, sir.
Right. So now I will just understand that you have drawn a small box which is called let, which is a lookup table. The second box is the one which we are drawing on top of it, which is called as an ALM, which is called as adaptive logic module. So first we should know what is let, and the let will go inside the ALM. That's all. Now what is present inside the ALM is the lookup table plus adder plus register. That's all will be there. But then what is very important for us to understand in this junction is, let me just explain that to you. Now I have 10 boxes of ALM. Okay. I take this 10 boxes of ALM and I am combining that together. So 10 ALMs are combined together. After that, what I'm going to get is called as a logic array block, which is called as an LAB. A logic array block is one which is consisting of 10 ALMs. Group of 10 ALMs is called logic array block. So what we need to understand, we should draw 3 boxes here. The first box is called as the lookup table, and that lookup table will go inside the ALM, and you will come to know that that ALM will go inside an LAB. So these are the 3 things we should understand in Intel FPGAs. Logic array block. Inside the logic array block, you will have the adaptive logic module. And inside the adaptive logic module, you will have the lookup table, which is the let. So what are the 3 things we should understand is the term called lookup table let, and the term called ALM, which is called as adaptive logic module. And the third one is called as the logic array block, which is an LAB. So when all these things combine together, how it look like, that's what I'm going to show you right now. This will give a clear picture here. See here, this every box is called as LAB, which is called as logic array block. It is made up of 10 ALMs. It's a group of 10 ALMs. So when you double click this one box, you can see 10 ALMs. And inside this 10 ALM, you can see lookup table, adder, as well as registers. All those things are there. So this is your logic array block. Then you will have row interconnect, and then you will have segmented interconnect, everything. So these are the 3 important terms at this junction we should know, along with the basic memory and a DSP resource. All other things are required later, not immediately. Now what is very important for us is we have understood what is let, then what is ALM, and what is LAB. Okay. Now when we program a code, that means when we develop a VHDL or a Verilog or a system Verilog code, we are very much interested in seeing how many lookup tables it has taken. That means how many adaptive logic modules it has taken, right? Or it has how many LABs it has taken. That's what we wanted to see when you write a code, and we are interested in seeing the resource utilization, which provides you what is the basic context. This is one side. Now the first question is, I am writing a code. I can model pure combinational logic as well as sequential logic. That's fine. But the next question is, are there any other resources other than these resources when you say these are basic resources? The next important resource which we definitely require inside the FPGA is called as the memory resource, they say. Memory resource means you have an on-chip memory, which is called as a block memory, we say. You write a code for a memory, and the tool has to exactly take that memory. And it is an on-chip memory. It is a block RAM, so it can directly use that resource. Instead of building a memory using lookup tables and registers, you will have a block memory which is of 20 KB. Directly, the tool can take that memory. That is the advantage of another resource, which is called as a memory resource. The idea behind this memory resource is it can get configured as a RAM, a random access memory. It can get configured as a ROM or a read-only memory. It can also get configured as a single port RAM or a dual port RAM. As usual, it can also work as a single port ROM or a dual port ROM. In any way, how do you want it to configure? You can configure it. That is the second important resource which we need to come across. So the first resource is called as lookup table, LUT, followed by ALM, then followed by lab. You keep that on other side. Okay. Lookup table, ALM, lab. That is one basic resource. Then the second important resource is called as the memory resource. Right. And the third important resource, for example, your code is using a digital signal processing application. Then we require a multiplier and an accumulate unit because you need to multiply and you need to add. So when you need to multiply and you need any questions you have, please. Shall I continue?
Yes, sir. Yes, sir.
Yeah, okay. So now you have, for example, you have a DSP application where you wanted to use a dedicated multiplier and an adder. So you wanted to perform multiplication and addition. So you multiply, add, and that should go to a register. So now you have an application where you require a dedicated multiplier, then we can use that. So what are the resources we have now? Lookup table, ALM, and then LAB, that is one resource. You have a memory resource. You also have a DSP resource. Along with these resources, you also have clocking and IO resources, which I will explain about those things later. Okay, but at this junction, right, basically what is required in an FPGA, if you ask, if you wanted to understand, then we should know about these resources. Right, this will give you a clear picture what is present in the internal architecture. There are so many things which we are going to discuss, but I'm going to give you a small highlight. That's what I just wanted to show you, a small glimpse. What is present inside an FPGA? If someone asks what are the components that are present inside an FPGA, then you should get at least some idea, some basic resources like lookup table and then ALM, etc. Then you should know about the memory resources as well as the DSP resources. Right. Now I have all these resources. Then blocks are connected with custom routing determined by your code. So that means I need to connect them. You can see there are different colors. One may be a memory resource, one may be a DSP resource, one may be a lookup table resource, right? So ALM resource. All these resources are connected together because in your digital design, you may require all these resources to perform a specific function. That's what is written here. Blocks are connected with custom routing determined by your. That's the base thought process. Okay, now what is an FPGA? What are the resources that are present inside an FPGA? That's what we have seen. Now the next question is why, right? Because we wanted to learn everything with why, then it is easy for us to move on to how do we use that. The next question that need to be answered is what are the benefits of FPGA, right? Now if you see what are the benefits of FPGA, it is reprogrammable and it is flexible. Second thing is it is product longevity. Whenever you have an FPGA, you will have that product for support for 10 to 15 years. The product longevity, it won't get changed immediately. The third very important advantage is the reduced time to market. When compared to ASIC design flow, the time to market is very limited, very less, right, when compared to ASIC. And the fourth one is called as the market size optimized. You have a specific market for FPGA that could be very, very easy for us to optimize it and use it for FPGA logic. So what are the things that need to be noted down here when you say it is reprogrammable and flexible and reduced time to market? So that is very, very important for us to get into it. Okay, what are the benefits we have seen? Next thing is what are the applications? Okay, where do we use this? That's just the kind of question which you may get. So what are the applications of FPGA? When you see the FPGA market, so consumer and automotive applications, test, measurement, and medical applications, communications and broadcast applications, military and industrial applications, and computer and storage applications. And all these applications we could use. Now, we can also have subdivisions here where you can use that for entertainment as well as for automotive. You know about ADAS and all those applications where we use FPGAs. Instrumentation, wireless, networking, wireline, and broadcast applications, military and security energy management applications, computers, storage and office automation, all these applications, we use FPGAs. Right? I have just brought only little information, right? We have many domain areas where we use FPGAs. Right. Any questions so far? Whatever we have seen so far, so that I will tell you how do we take from the spec to the FPGA. Do you have any other questions? No questions? Shall I continue?
This is the limited block in the DSP block, sir.
Good question, but it depends on the kind of family what we use, right? Because when it is a small family like Max 10, you will have limited number of 9-bit multipliers. But then when you go for the Stratix or Agilex devices, which are high-end devices, then you will have more number of DSP blocks, right? They are meant for high density and high speed applications. Okay, I can show that to you. Yeah.
Okay.
Yeah. I'm going to explain about the family of FPGAs. During that time when we discuss about them, I'll show you what. Yeah. Now, what is very important? So
Hello?
what is the key? Yes.
Yes, sir. You mentioned that that block of code should connect. No, sir. That what we are writing, the code should connect this LUT table and adaptive logic. How it's that? Yes.
Right. Because it will take. It is like a kind of a placement and routing, right? The FPGA tool has a process called a fitter, which is called as placement and routing, right? So it is going to place the components. For example, your code require one memory, one DSP block, and one ALM, like that you imagine, right? You write a code which requires these three.
Yes,
Now, there is a process called placement and routing inside the FPGA design flow. So what it will do is it will select the components. It will select in the mind, right? This is the RAM and this is the DSP and this is the lookup table. So it will start performing interconnections between them. That interconnection is called as routing. Okay. Once it makes connections between them, right, we will come to know that they are going to get configured for our device. So that how that process happens, I will show to you in the demonstration.
Okay, sir. Thank you.
Yeah. Are there any other questions before we get into this stage? Okay, so this is like a initial class, right? I cannot bring all the things which we can, right? So that I'll just put glimpse on whatever required. So that once I start showing you the simple demo, you will come to know what is happening inside the FPGA design. Okay, if somebody gives you the specification, what will happen? Once the specification is given to you, we will be writing the code. You will write the code in VHDL, you will write the code in Verilog, or you will write the code in System Verilog, whatever. So after you write the code, we will use the Intel Quartus Prime Design software. So this is the tool which we are going to use in the course. Using this Intel Quartus Prime Design software, we are going to perform the simulation, synthesis, filter, all the operations, whatever I have mentioned. Then we are going to generate the bitstream file, which is called as the SRAM object file, and we implement the design onto the FPGA. This is the step we are going to do. So we will have the spec ready. Once the specification is ready, we will write the code. And we will take that code to the Intel Quartus Prime Design software, perform simulation, synthesis, all the process what are available there, and then we program that onto the FPGA. That means specification to HDL to programmed FPGA. That's the base start process. Okay, then can we expand it further when you say? Definitely possible. That's what we are going to do now. So how do we expand it? When you say, first we develop the code. Then what we do? We perform behavioral simulation. Behavioral simulation means we are going to write a small test bench to verify the functionality of the design. Okay. So once we pass some test vectors and verify the functionality, then we synthesize that code. So now what is simulation? If you say, simulation is the process in which the functionality of the design is verified by passing suitable test vectors. So I am going to pass some test vectors, and by that I will come to know whether the functionality of the design is correct. Okay, you write some code, you write some test bench, you pass some test vectors, verify the functionality. That's one side. But what is the guarantee? The code what you have written provides the exact hardware, right? Exact schematic. That's what we have a doubt. In order to do that process, we perform synthesis. Synthesis is a process in which the HDL code is translated into equivalent gate level schematic. The code, whatever you write, we are going to translate that into equivalent gate level schematic. You will come to know that whether it is providing the correct hardware. Okay, that is one side. So you check the simulation, you check the functionality. Second thing is you do synthesis and verify whether it is providing the correct hardware. Right? Then another important step is called as the placement and routing, which I mentioned earlier. You have to place the components and you need to route the components. You should make interconnections between them. Right? You will have AB, you will have CD, you will have Y. All need to be connected. Then comes a very important step is called as the timing analysis. Right? So the concept of timing analysis means what? Timing analysis is a method of analyzing, debugging, and validating the timing performance of a design. That means here in this case, we are verifying only the behavioral functionality. We are not performing timing. But what is very important for us is we also need to ensure that the design is not having any setup or hold violations, right? So we wanted the design to work at the desired frequency what we wanted. How do we ensure that the design is working at the desired frequency? When you say, then we will perform a process called as timing analysis. By performing this, we call this as timing closure because we wanted to close the design without any timing violations. That's what we call that as timing closure. You close the design without any violations. Okay. After that, what we are going to do is you take that design and implement that onto the FPGA. This is what we are going to do. This is for one block, right? Now, can I connect 5-6 blocks and then create a system? When you say yes, that's what we are going to do that with the help of a platform designer, which I showed you. You connect all the components together and you create a system and integrate that system and check for functionality. Okay, and using all the components which are available in an FPGA, can I generate a processor? That's what is the objective. So embedded system design using the processor. That's what is the logic. So how are we going to build a small block? Starting from that, how are we going to create a system and how do we use the resources which are inside the FPGA and how do we create a processor? All those things are our objectives. Now at this junction, first we should understand the traditional FPGA design process. So the traditional FPGA design process, the first thing starts with the coding. Then what we do is we do simulation. Then we do synthesis. Then we do placement and routing. Then we need to ensure that the design is not having any timing violations. Okay, are there any violations? Yes, if there are some violations, then what to do? When you say, there are different techniques that are available inside the Quartus Prime design software, which will ensure that how do you overcome those violations, right? That's called as timing closure. because it is not very easy that, okay, you apply some timing constraints, the design will meet timing, right? It may not sometimes. So in that case, we will definitely come to know that what are the different steps. Right. Now let us see the products. Okay, what we are going to discuss is some family, but we need to understand what are the different family devices that are available. Okay. Our focus would be on the Intel Max 10, which is called as the low-end and low-cost FPGA. So now if you see the Intel FPGA products, you can see Intel Max 10, which is the low-end I told you. And then you have Cyclone. So these two are the low-end and low-cost FPGAs. And then you have ARIA, which is our mid-range FPGA. And the Stratix and Agilex devices are our high-end FPGAs. So the Intel Max 10 is our 55 nanometer, Cyclone, which is our 28 nanometer, ARIA, which is 20 nanometer, Stratix, which is 14 nanometer, and Agilex, which is 10 nanometer. So now the idea is each and every FPGA is meant for different set of applications. We wanted a specific application drive target, then we can choose different set of FPGAs here. So the idea here, if you see, you have lowest cost and lowest power. Cost or power balance, because it is an SoC, that means it has a processor inside it and transceivers. And you have mid-range, and then you can see they are optimized for high bandwidth, you can see. What are the tools that are available? So our focus is on the Intel Quartus Prime Design software in this course. But you can see there are soft core as well as hardcore. The meaning here, hardcore means you have a processor which is embedded inside the FPGA, which is inserted inside the FPGA fabric. We call that as a hardcore processor, which is called as a hard processor system. Inside the FPGA chip itself, you will have a processor. You will have a dual core ARM Cortex A9 or a quad core application processor A53 based on the set of families. Right? But what is NIAS2 when you say it is a soft core processor which is going to use the resources which are present inside the FPGA, I told you. And along with that, are we going to write code at all times when you say no, right? Sometimes we don't need to write the code because I can use the intellectual property IP which is available. So what is an IP? When you say they are pre-designed, they are pre-tested, and they are pre-verified, so that you don't need to generate it, you don't need to test it, you don't need to verify it. You can directly instantiate that to your design, and you can use it for industrial applications, computing applications, enterprise applications, wherever you want. Okay, now at this junction, what is the basic thought process is, I have given the set of family products, but then what is the greatest advantage of them? What are the specific features of all of them? When you say that, I have brought in this slide. You can see from the low cost to low end device to the high bandwidth device, it has been given. So Max, Cyclone, ARIA, Stratix, and Agilex. Right? As I mentioned earlier, our focus would be on the Max 10 device. We are going to target it, and then we are going to implement based on those things. Okay, what are the specific features when you say they are flexible, multifunctional reprogrammable silicon, custom hardware functionality, bare metal speed and reliability, and they are truly parallel in nature. That means you are going to write HDLs, which they are concurrent in nature. Therefore, it is very easy for us to write the code which are parallel, which you can help you to achieve more speed. Okay, now the next question that need to be answered is, I have so many FPGAs that is available, different families, but how do I choose the corresponding FPGA for the corresponding application? That's the kind of question you will have. Multiple FPGAs are there. To solve that, right, you have different logic here. This is what is that, okay? There are so many things in the slide, but while going through the different set of sessions, we are going to focus on particular area, right? Since it is an introductory section that has been given to you to get a broad perspective what is available. Okay, don't get confused by many things, right? Because we are going to focus on a narrow down area, and then we are going to see application logic. But when we are very clear that this is my application, then you can choose the corresponding FPGA for that application. For example, if you say Intel Max 10 device, which I mentioned, a low-cost device, you can use it for automobile sensors, traffic sensors, IO expansion, edge computing, etc., board management. Right? The main application set of logic, sensors and edge devices. Right? It has an ADC inbuilt so that you can use it for the data acquisition logic also. And you can see vision systems and purpose-built application-specific hardware. So what is the main set of applications? Machine vision, embedded vision, robotics. We have a DE10 nano device, which is called as an IoT edge device. And it is also called as a robotic device, right, which can be useful for robotic applications. And then ARIA device, which is our mid-range device, which could be useful for data center, networking, military and defense, as well as the ADAS applications. Then the Stratix and Agilex devices, which are called as high-end FPGAs, the main applications are on the cloud, data center, and high-performance computing applications, and on the 5G wireless applications, military and defense, all those applications we use that. So that means it shows that the right performance and features for the right set of applications. So what is the key takeaway till this place when you say, we have seen what are the components that are present inside the FPGA, starting from ALM, lookup table, etc., till the DSP resources. Then we have seen what are the benefits of FPGA, what are the applications of FPGA in general. Then we have been specific to Intel FPGAs, what is present inside the Intel FPGA. That means what are the different set of families. Now, if we closely look into the architecture of a Max 10 device, right, as a low-cost device, then you can see that it has memory resources, RAM blocks. It has DSP resources, which is useful for multiplication. It has up to 50K logic elements. That means you can see one logic element is equivalent to one 4-input lookup table plus one register. That means you can see that this is up to 50K logic elements. You can see the density of the FPGA. How much is it? Then we can see it has DSP blocks and it also has the memory blocks. So you can see DSP memory. And you can see it has a NIAS to 32-bit processor, which is a soft core processor. And all these resources I explained, basic resources, memory resources, DSP resources. Along with that, you can see clocking resources. You can see PLL. And then you can also see IO resources, which is your IO resource. You can see that here, 8 IO banks, which is IO resources. Along with that, you can see 12-bit successive approximation register ADCs that are available. And then you have a user flash memory, which is called UFO. So all those things are there. While going forward, in each and every section, we will just specifically understand what is present inside each and every device and how they are going to help us. But now you can see that this is a Max 10 FPGA, and we are going to target it for a specific application, let us assume. Then we need to understand what are the resources that are present inside this device. So you can see it has 50K logic elements. That's what we require for lookup table and then ALM operations. Then we need to understand it has memory resources. It has DSP resources. And then it also has the soft core processor, where you can create an embedded system using the soft core processor. And you can see clocking resources, IO resources, and then it also has the ADC information. Now, slightly moving on to the other device, like for example, I told you about Max and Cyclone, right? Now, I mentioned that it is an SoC FPGA. What is the meaning is, in this FPGA device, you don't have a dedicated processor which is immersed inside the FPGA fabric, right? Whereas in the Cyclone device, which we are going to see now, you can see there is a dedicated place, right? You can see it has a dual core ARM Cortex A9 that is present inside the FPGA fabric. That means you have basic resources, lookup table and other resources, distributed memory. Distributed memory means the memory which is constructed using the logic array block, which is called as MLAB. That is called as distributed memory. So you have ALM, you have memory blocks, you have digital signal processing blocks, you have clocking resources, you have IO resources, right? And you also have a dual core ARM Cortex A9 that is immersed inside the FPGA. It also has the processor. All those things are present inside one single FPGA. That means you can understand that, okay, where we can use this application, FPGAs, we can use it for a high-speed embedded computing platform. That means it can be used for SoC applications. Right? So why do we call this as hard processor system? Because you can see there is a processor which is immersed inside the fabric. So that is not there in the Max 10 device, which we are going to use today, because it has a soft core processor. That means it is going to use the FPGA resources and build a processor. Whereas in the Cyclone device, you already have a processor which is immersed inside the FPGA fabric, along with the memory resources, DSP resources, etc. You also have a processor. So what is the greatest advantage? When the processor is immersed inside the FPGA fabric, that is going to give you a powerful embedded computing platform where we can use it for SoC applications, the system on a chip applications. Right, now let us just get a high level description and then I will move on, like how we are going to do it. So now it's like a complete theory logic. But then how are we going to use these FPGAs, right? That's the second section which we need to get into. Why questions we answered. Now we need to see the how. How are we going to do that? To get into that, first we should understand how do you design for an FPGA. When we need to design for an FPGA, first you should have a design idea. We write a code. Then we require a software. That is very important. I am aware of HDL. I know how to write VHDL Verilog or system Verilog code for a digital design. But I want a software too to execute it, right? So that means we require a tool which will help you to execute it. Then we should do synthesis and placement route everything. And we generate the programming file. And then we implement the design onto the FPGA. So how do you design for an FPGA? So how do you design? You have the idea, you develop the code, then you use the Intel Cortex Prime design software, generate the bit stream, the SRAM object file, and then we implement that onto the board. Okay, so to do that, what is very important for us is like what is the different set of entry. Either you can write the Verilog, VHDL as well as system Verilog, or a state machine or a schematic entry, right? So we are going to focus on how do we use this RTL code. Then we can, when we enter into the IP core, right, IP catalog, then we can understand how do we directly instantiate the IP and then create the design. So you can see that the Verilog code is available there on the right hand side, which shows you that there is a code that is written. We take that code and then we are going to understand the flow, how it works inside the Cortex. We do synthesis, filter everything and generate the process. So this is the way how that could be done. Now the idea is how this is done is the step which we are going to see. Before that, this is our focus. What is the focus of this course? We take a design. That means you are going to write the code. You are going to check the syntax and ensure that there is no syntax or semantic errors. We perform analysis and elaboration. Then we are going to ensure that the design is not having any functional errors. That means we need to perform the functional simulation. So functional simulation is the process in which the functionality of the design is verified by passing suitable test vectors I mentioned. Do that. Then we do synthesis. Before we do synthesis, what I also mentioned is you have to ensure that you do proper pin planning. That means your FPGA chip will have some pins that are dedicated pins, right? You need to do pin planning, right? Or you need to apply pin constraints. Along with that, you also need to apply timing constraints. That's what we are going to learn. What are the different set of timing constraints? After you apply constraints, we do synthesis, we do fitter, we generate the programming file, implement the design onto the FPGA. Right? Then we need to ensure that the design is not having any timing violations. That's what is called as the timing analysis. So this is the entire design flow which we are going to learn through the course. So this will give you a fair idea, like where do we start? Starting from the design idea, and how do we implement the design onto the board. That's the base principle here. So where it is very critical for us to understand is the synthesis process and the fitter process. This is very important for us to understand. What happens during synthesis? Because this is the place where you can apply different set of synthesis optimization, synthesis techniques, like you will have multiple things which we can do. And the second important process is called as the fitter, which I mentioned as a placement and routing. When you do placement and routing, what are the things that are happening? That we need to understand. So we need to spend some time in understanding all the options there. What are the different HDL coding techniques that we need to take into account? There are multiple things which we need to do. Right? But for all these things, what we are going to use is called as the Quartus Prime design software. There are two things we need to learn before we get into the detail. One is, how do we download and install that software? And what is the corresponding device library, right? For example, we wanted to use only Max10 device. What is the data sheet of the Max10 device? Where is the user manual? From where we can download that? And how do we go ahead with the exercise? So I'm going to explain you all those things in detail. That will give you a clear picture so that if you have the tool with you, you can practice on your own. Right? So before getting into the next step, let me start with that. And then I will come back to this, right? So let me first show you, right? This is important for you to understand. After getting into the details, we can go back. The Quartus Prime design software, which we are going to use in our course, comes up with three editions. One is called as Light Edition. The other one is called as Standard Edition. And the third one is called as Pro Edition. What we are going to use is called as the Light Edition, because this Light Edition does not require any license. Whereas the Standard Edition and the Pro Edition requires license, because the Standard Edition has the support of ARIA 10, that is a mid-range FPGA, and the Pro Edition has the support of Stratix and Agilex devices. Whereas the Light Edition, which we are going to use, will have the support only for the low-end and low-cost FPGAs, which is our Max10 and Cyclone 5. Since our course is targeted for the Max10 and Cyclone 5 devices, we don't need to have any standard or Pro Edition with a licensing logic. You can use the Light Edition, which does not ask you for a license. Right? That's the base logic. So the first thing is, you require a software that will help you to create a project from scratch, starting from empty project. And then that will help you to build whatever you want in terms of VHDL Verilog or System Verilog. Then from there, it is easy for us to perform simulation, synthesis, fitter, as well as the generating the programming files. Okay, where this software is available, how do we download these things? Okay, all those informations. Let me spend some time here. Before getting into those details, are there any questions that need to be answered? Please let me know. Do you have any questions till this what we have discussed? Before I show one demonstration with a simple example.
Sir, for example, like FPGAs, like Intel and other, there are Xilinx and other companies also. Is there any only basic difference, or is there any like various difference? What is the main difference? almost same, or it has any more difference in other?
Right. So generally the tool flows, right, will look similar, right? Exactly the similar. See, any FPGA you take, it is going to perform simulation, synthesis, right? And then optimization, filter, etc. Right? But what are the algorithms that are present inside? That may differ, right? We cannot say that the same algorithms would be present inside the synthesis and filter logic. And especially the family devices will also vary, right? For example, how do we call this as an SoC FPGA? Like that, Xilinx will also have an SoC FPGA like Zinc, Z-board, different things they will have, right? Similarly, lattice semiconductor will also have. So the idea behind this is like the flow will look similar. When I say FPGA design flow, whatever I discussed in the first initial slides before I start Intel, it is exactly same for any kind of vendors. But when we are very specific to Quartus, I can explain that what are the Quartus features rather than what is available in Vivado or any other tool. Is that clear?
Yeah. Okay, sir. Fine.
Right. And another important thing is, if you are familiar with what the FPGA design flow, it is very easy for us to switch to any other flow.
Okay.
It doesn't mean that it is not possible. For example, Xilinx FPGAs to Intel FPGA design conversion is possible. And then you can also do the vice versa of that.
Oh, okay. Okay, sir. Fine.
Are there any other questions?
Hello, sir.
Yes.
Yes, sir. That Intel Cortex software is using for synthesis purpose. What about that model sim, sir?
Good question. So that's what I'm going to update you right now. The Intel Quartus Prime Design Software Lite Edition uses a model sim Intel FPGA Starter Edition, which comes along with Quartus, so that you don't need to install it separately. So you can use model sim for simulation, and you can do synthesis and filter operation directly with the Quartus. Even though it has some third-party support, with the Lite Edition, you have the model sim. There is no worry.
That means model sim is used for a simulation purpose.
Yes, model sim is used for simulation purpose. You are right.
Yes, sir.
Okay. Thank you. Are there any other questions before I start the download center? Thank you very much. It's very good interaction, right? And there are questions, are very right questions, right? Let us move on to the next important thing. So if you go to the, yes, please continue. Yeah.
You told this higher bandwidth of this latest FPGA like Statix, Agilex. And this means what are the so many higher bandwidth, and it may be number of IOs will be more, and the additional feature will be there, sir.
Additional feature will be there. For example, transceivers. For example, starting from 26 gig, right? The transceivers that are available in Agilex devices will go for 58 gig or 116 gig. That kind of capability may not be there with Cyclone 5 devices, right? And also the DSP capabilities, number of DSP multipliers that are available in Cyclone 5, right? Which will be very less. That may not be there with Agilex. Will be having more, right? More DSP capabilities, more high bandwidth memory, more number of transceiver capability will be there in the high bandwidth devices.
Okay, sir.
Right? Yeah, sure. In the second week or third week, when I explain about the different architectures or different devices, specifically when we get into, then I will show you what are the different capabilities, so that you will get a comparison of all the devices.
Okay, sir. Thank you.
Yeah. Right. Because the focus of today's is like I want to show a glimpse of everything, but in every week we will narrow down and go in detail.
Yes, sir.
Right.
Thank you.
Yeah. Welcome. Right. So I hope we can continue with this. Like, let me just explain you what we need to do. Right. So just go to the download center for Intel FPGAs. So you just say download center for FPGAs or download center for Intel FPGAs. So the moment you open this FPGA software download center Intel, you all need to go to this site. When we go to FPGA download center Intel, right? When you are doing this for the first time, it may ask you to create one sign-in with small credentials. You can give your username and password, and then you can create it. Okay? This is just to understand that who is downloading and using that software. There is nothing to worry about it. Okay. So when we enter into this FPGA software download center, it will show you the download center logic. So as I mentioned earlier, there are 3 different editions. You can see on the left hand side, it shows like Pro, Standard, as well as the Lite edition. But at this junction, as I mentioned, we wanted to use only the Lite edition. Okay. So the moment you enter into the FPGA software download center, on the left hand side, you can see Intel Quartus Prime Design Software. So just click that. And you can see in the Pro edition, you have 97. And in Standard, you have 45. And Lite, you have 19 is there. Okay, these are the different editions, which is different versions which it has. So just click here, Intel Quartus Prime Lite edition. Okay. And what I suggest you is don't directly go for the higher version. Okay. We can start with the middle version. And I will tell you like when do we need to use the higher version, because higher version uses the different set of simulation tools. Like instead of Model Sim, you have Questa, right? But let us start with Model Sim. Then I will tell you when you can download the latest version so that you can get the Questa features also. So let us start with the middle version, which is like you start with either 18.0 or 18.1. So this will have the features which are starting with basic Model Sim simulation. Then later, if you start downloading the 21.1.1, which is the latest version, which has the support for Questa. I will show both, but I request you to download either 18.0 or 18.1 Lite edition. So the moment you click here, 18.1 for Windows, right? The moment you click this software, it will automatically take you to the page. You can see here, Intel Quartus Prime Lite Edition Design Software version 18.1 for Windows. If it is Windows, you download Windows. If it is for Linux operating system, you click the Linux. Okay, right? If it is for Windows, I'll just show that to you. You can see that download. It shows Quartus Lite. Okay, it shows 5.8 GB. The advantage of this is which is available as a 5.8 GB. I have clicked it there with the mouse. You can see that. It shows Intel Quartus Prime Lite Edition. In bracket, you can see free. And Model Sim Intel FPGA Starter Edition. You can see in bracket, it is free. So therefore, you can use the Lite Edition Intel Quartus Prime Design Software for free, along with the simulation for Model Sim as free. Because the simulation software, the Model Sim Intel FPGA Starter Edition, is also available with this download, so that you don't need to download it separately. Okay. And another important thing that need to be noted down is ARIA2, Cyclone 4, Cyclone 10 LP, Cyclone 5, Max 5 and Max 10 FPGA. All these devices library support is also available in this download. You don't need to download any specific library support. That means I'm going to use only Max 10 and Cyclone 5 for this project. If you say, then you can just use this Lite edition because Cyclone 5 library support is also there. Max 10 FPGA is also there. So this is for the multiple download. Okay, the moment you click this multiple download, you will get a tar file. I request you to download this. Okay, after you download, what we are going to do, right? The idea is once we download this software, right, you will have, you can see that. Okay, so you can see this is the version and what is included also I showed you. Okay, once we download, how it look like, I'll show you. For example, you go to the C drive and then I say Intel FPGA Lite. So if you go through this, you will have like this. Okay, inside this folder, you can see Quartus, where you can see all the like DSP builder, you will have HLS, high-level synthesis, all those things will be there along with this. You can see high-level synthesis, HLS is here, right? So inside the Quartus, right, you will have all these folder. Informations will be there. Okay, you need to just run that setup.batch file. That will help you to do the process. Okay, how do we install it? When you say download the tar file, extract the files into the same temporary directory. Just put that in a C drive and then run the setup.batch file. That's all. Once you run that setup.batch file, it will ask you at the end, okay, do we want to keep the Quartus Prime Lite Edition software in the desktop shortcut? You can say yes, so that that will be available in the desktop only, so that you can open it and use it. And sometimes what will happen, I will tell you. I don't want to get the library support for all the devices. I don't want, for example, Cyclone 4 or Max 2 or Max 5. I'm not going to use, right? I'm going to use only 2 devices. Why I need to download everything when you feel like that? There is another way to solve this problem, which is called as individual files. When you click these individual files, it shows Model Sim Intel FPGA Starter Edition. So you can download Model Sim only separately and then Quartus separately. So you can install Quartus and you can install Model Sim. Okay, so this is 1.7 GB and this is 1.1. Okay, now I have only one FPGA device with me. I have only Max 10. Let us assume when you say, then you need to download only that Max 10 device support. You don't need to download anything. Okay, that means you need to have only 3. First, Quartus Lite setup, Model Sim. So 1.7 plus 1.1 plus you can take this 330.9 MB. That's your wish. You can follow any method. If you directly click multiple download, you have 5.8 GB in which everything is there. You don't need to install anything separately. To avoid that confusion, you can just download one bundle and then install it. So that tomorrow, if you are going to use Cyclone 4 or you are going to use Max 5, then there is no need to worry because the same device will work. If not, every time you need to install the corresponding library support. But at this junction, since we are aware that what is the FPGA device we are going to use, I suggest you any method is fine for you. Okay. This is the thing which you need to do. This will help you to have the software ready. And it is very easy for us to perform simulation, synthesis, everything at your end. Only thing is you need to implement onto the board. That time you require the board. All other steps, right, till compilation, the final step requires the board, right? All other steps we can do in our local system only. That will give you a fair idea how to integrate the design, how to integrate IP, how do we develop a test bench. All those process you can learn on your own when you have the software ready with you. And while compiling, you will come to know like what are the kind of errors we are getting and how are we going to sort out these things, because multiple people will have multiple kind of errors. Then we can understand the concept of debugging also better. Okay, so first thing is click multiple download. Second thing is individual files. Anything is fine, right? And the additional software tab has some things which are required for it. For example, when you are doing programming for the first time, right, you can use this Intel Quartus Prime Programmer and tools. Only that time you can download it and use it. But all these things are there. But easiest way is go to multiple download and then you can download this. In the bracket, you can see it shows device support included, so that you don't need to download or install any device support separately. And as I mentioned earlier, the Quartus Prime Lite Edition software is going to support only Max 10 and Cyclone 5 devices. That means Cyclone devices. Right, this is the one important page which you need to look into. The second page what we need to look into is the user manual. Okay, so DE10 Lite user manual. I'll just show that to you. So this DE10 Lite is the board which is based on Max 10, right? So that is the one which we are going to go to. So just you can type in Google DE10 Lite manual, which will automatically take you to the Terasip website, and you can see that. So this is the manual. So what is required when you say this DE10 Lite board, which is based on the Max 10 device, has 10 LEDs and then 10 switch buttons and 6 hexadecimal displays. And it is ideal for all digital system design applications. And we can start with this board, which is the basic one. And what is important for us to understand in this case is, now you can see this is the board, right? And you can see like it has LEDs, switches, etc. While creating a project into the Quartus Prime design software, we need to know the device family, how to filter it, right? Generally, we'll do that. For that, we need to know what is the family device. That's what is specified here, right? 10M50. 10M means Max 10. 50 means 50K logic elements. This is the package DAF. 484 means 484 pins are there. C means commercial. 7 means speed grade. And then general. All those things are available in the data sheet. You don't need to worry about that in today's class. Okay, we can go through that and learn later. But idea is we need to know that which device we are targeting. That means while creating the project, we should know what is the family filter. Okay, without knowing that also, can we do that? Yes, no problem. You can just copy and then paste it while creating the project. And then you can learn later, like what is the specific details of each one of them. Right? What is the basic idea? We are going to target it for Maxton device. And then we are going to create a project. We do simulation, synthesis, filter, everything. And finally, I wanted to implement my design onto this board, which is, you can see here, it shows Altera Maxton. Right? And you can see this is from Terasic. So what are the two things you should have? First thing is, you should go to Download Center for Intel FPGAs, download the Intel Quartus Prime Lite Edition software 18.0 or 18.1, not the latest one. Okay, what will be wrong when you say? There is nothing wrong, but the way that is invoked, the Questa and the paths will be completely different than how do we do with model sim. So when I show something and you are trying to do something, there won't be any sync. Okay. In the last class, I will also show you that how do we use that with Questa also, nothing wrong. So that while integrating a Questa project for system Verilog, you can use that. That is available with Lite Edition also. Nothing wrong to use that. But the initial classes start with model sim, and later we can try to see how that could be integrated with the Questa also. So two things: download and install the software one, and have the DE10 Lite user manual handy with you. So at any point of time, this will be useful. Okay. What are the other things when you say? In this user manual, you could also see what is the pin constraints, right? For each and every LED switch, etc. Right? So for that, we don't need to search anywhere. It is available in the user manual itself. For example, I will show that to you. So this is our switch. There are 10 switches in the DE10 Lite board. You can see that what are the pin configurations. So it will be very, very easy for us to do pin configuration here. So SW0 is what is the pin number, right? Till SW9. This is for switches. This is the IO voltage. Same is available for the LEDs. How to use the LEDs. If you wanted to use it for hexadecimal displays, it is available. X0, X1, X2, X3, X4, X5, X6, all the things are available. Right? All these things, pin configurations are available. But at this junction, we are going to concentrate on switch, LEDs, and then hexadecimal displays. Later, whenever required, you can go through and see other IOs. But at this junction, we should know that what is the specific family filter and what are the basic pin constraints that need to be applied while creating a project. So these are the things that we should have it handy. Other things I'm going to explain that one by one. During the class, we can try, or you can try it later also. Right? Any other questions you have before I start one small example for you? So this is the place where we need to start the Intel Quartus Prime Design software. A quick, small demo I'm going to show you. Do you have any questions before that? Shall I go ahead? Any questions? Okay. Assuming there are no questions, let me move forward. Okay. So the moment you install the Quartus Prime Design software, right? For example, this is, you can see the desktop, it shows Quartus Prime Design software Lite Edition. So you open the software. Now, the moment you open the software, you can see it shows Project Navigator, and then you can see compilation tasks here and the message window here. And on the right-hand side, you can see that the IP categories, the intellectual properties are available. Now, this is the Quartus Prime Lite Edition window. Now, we are going to create a new project wizard now. We are going to create a new project wizard. On the other side, you can see open project. What is the fundamental difference? I'll tell you. When it is a new project wizard, you are going to create the project from scratch. That's what we call that as a new project wizard. When we say that as an open project, then we are going to open an already existing project. That's what we call this as an open project. Right? And then what is recent project? When you say the projects which we opened recently. So this open project means you have done that a week before. It is not listed here. Then you can click open project and open that project which we have done 1 week before. The recent projects are projects which we opened some time back, maybe yesterday or today morning something. You can just directly click it and open that project. But our objective is not of those two methods. We don't want to open a project which has been created earlier. And we also don't want to see a recent project. What we wanted right now is to create a new project that we need to create from scratch. When we are going to create a project from scratch, then how do we do that? That's what we need to understand. Right? There are many question marks, ifs and buts while doing this. Don't worry about that. All those things would be known to you during this course, right? And you may not get everything on the first day, but I wanted to show you the flow, what is happening, so that you can get connected to it. This is the way we are going to learn. This is the logic that is behind it, like that, okay? So let us start with a new project wizard. When you say, what is this new project wizard? The moment you click it, what it shows is the new project wizard helps you to create a new project and the preliminary project settings, including the following. Whenever you click a new project, we need to give the name of the project. You need to give the name of the top level design entity. You want to give project files and libraries, whatever you want, right? Target device. What is important is you should know the name of the project. What do you want to call that? You should know. What is the name of the top level design entity? It can be an adder, multiplexer, whatever you want, right? And then what is very important is the target device family and device. So which is the device? That's what I asked you to download the Max 10 DE10 Lite device user manual, because we need to specify that family device while creating the project, because you cannot take specific logic, right? You need to implement that onto the board. So that means we should know what is the device that we are targeting while creating the project. Okay, and the last one is called as EDA tool settings. This EDA tool settings is very important for selecting the simulation tool and the synthesis tools, right? Sometimes you may need to use a third-party simulation tool, and then you may need to use a third-party synthesis tool like Simplify Pro, etc. Then we should know what is the kind of tool we are using and how do we provide those executable paths. Okay, that is important now. So first it comes to the introduction page. What we should say is say next. Okay. In this place, it is asking you what is the working directory for this project and what is the name of this project it shows, and shows what is the name of the top level design entity. While it is VHDL or Verilog, what is our main thought process is like what is the name of the entity, right? That is the name we will try to store that as a file name, right? So what is very clear is like we need to know what is the name of the project and what is the name of the design file which you wanted to save it. That is very critical and important for us to understand. Okay, what is the working directory? That may be a new directory which you are creating. And then you may need to create a new Verilog or a VHDL file here. That's what is the specific scenario here. Okay, what is the working directory for this project? So in the C drive, I'm creating a test example. Okay, so for example, you say, I wanted to come up with a simple example here. So example 1. And then you say design, right? So some design you take. Now, what is the name of this project? So you wanted to start with an adder or a subtractor or a multiplier or a counter, whatever you want, right? So I need to provide what is the name of this project. So that I need to specify, for example, adder. What is the name of this project I mentioned? That would be my name of our top level design entity. So what is the working directory of this project? I have provided some name, example 1 design. And what is the name of this project is the module name which I wanted to have in my code. So it is an adder code. The moment you say next, so it is showing that there is no specific directory like that. That means it's a new directory. You are creating a new directory. Inside that, you are creating a new file. So what it is showing is there is no directory called example1 design. Do you want to create it? It shows. So we should say yes, please create it. That's what we wanted to ensure. So once we say that yes, do you want to create it? Say yes. Now when we do that, it shows an empty project. This is the place where we have to be very, very careful. The first one is called as empty project. Empty project means we are going to do everything from scratch. That's what we call that as an empty project. That means we are going to specify project file. We are going to specify the library. We are going to specify the target device family, device, EDA tool, etc. Everything from scratch we are going to specify. That is called as empty project. There is another one which is called as a project template. That means they are already available. You don't need to create anything from scratch. They are already available as a template. You need to take that template and use it in your code. Okay. The second one is not required at this junction because we really don't know how to create a project and then how to perform synthesis, filter, etc. Right? In that scenario, we really don't know how to reuse that template also. So after getting some experience in creating a project, how to design and reuse, then this project template section may be very useful for the Quartus engineer. So at this junction, we start with the empty project because we are going to create everything from scratch. So what we have done, we created a directory and then we have given some module name as adder. That's what we specified. And you can click next. Okay. So the moment you click next, okay, this I will explain you in detail, which is very important for you to understand. When we click here, add files, right? You may need to create a hierarchical design sometimes. So that means you will create an off adder and using that off adder, you will create a full adder. Using that full adder, you will create a 4-bit full adder, and using that 4-bit full adder, you will design a 4x4 multiplier. And using that 4x4 multiplier, you will design an ALE. Let us assume like that. Anyway, our objective is also like that only. You are going to reuse. But when you need to do that, you need to add the files which are required for this project. But then since everything is new, right, we are going to create everything from scratch. This particular wizard may not be very useful for us at this junction because add files, when you say now we are going to create a new file, how do we add it? We cannot. But now after creating this adder can be reused in the full adder. And that full adder can be reused in the ripple carry adder. Like that, the continuation can happen. But at this junction, since it is everything from scratch, this add files sections may not be useful for us. Okay, just skip that, say next. This is the place which we have to be very, very careful. Because since it is a light edition, as I mentioned earlier, it supports only Max and Cyclone devices. So you can see here, Max and Cyclone devices means when you bring this drag, right? When you drag this, you can see Max 5, Max 2, Max 10, Cyclone 5, Cyclone 4GX, Cyclone 4E, Cyclone 10 LP, and ARIA 2GX. Only these are the devices that can be supported in this edition. So there is, you cannot see any ARIA, right, 10 or Stratix 10 or Agilex, nothing here, right? Because it is only for low end. Now, what is our thought process is we need to use only the Max 10 device at this junction, okay? So select only the Max 10, which is our D10 light. Just select that. The moment you select Max 10, it is expecting that what is the family filter. You can see there are so many devices, but we need to select only one device from that. Okay, how do we select that? When you say, we have seen from the DE10 Lite user manual, what is the family filter detail. Either you can enter that or you can copy from the DE10 Lite user manual and paste it in this place. Both will work, nothing wrong. So the idea is I should know What is the family filter here? So 10M, 50, DAF, 484, and then C7G. This is what is the name. If you have seen in the user manual. I'm entering that directly here. 10M50, DAF, 484, C7G. Now I say, select the device, right? And then say next. So what is very important? You have to select the family, max 10. Then we should provide a family filter, name filter. The moment you enter the name filter here, you have to select that device and say next. Now this page is again very critically important, which is called as EDA tool settings. In the EDA tool settings, you can see there are different third-party simulation tools like ActiveHDL, Rivera Pro, Model Sim, Altera, Questa Sim, etc. Don't need to select anything at this junction. I will tell you where you can select it later. Okay. Similarly, at the synthesis stage, you can see Precision Synthesis, Simplify Pro. There are different tools, right? So don't touch anything at this junction. Let it be none only. Okay. Now we can say next, and you can get a summary page. So in the summary page, you can see when you click finish, the project will be created with the following settings, where you could see example 1 design is the name of the directory, and the project name and the top level design entity name is adder, and you can see the family name, family device, etc. Everything is proper. Now we can say finish. So you can see that it shows that please wait while Quartus is creating a project for you. After it creates a project, on the left hand side, you can see max 10. I can just show that, right? You can see max 10. And what is the module name you specified? That is also present there. Okay, now let me explain you how to create a project now. How do we create a file logic? Whether it can be Verilog or BHDL or system Verilog. Okay, now go to file and say new. So file, new. Click that. You will get a dialog box opening where you can see Verilog HDL file, BHDL file, and a system Verilog HDL file. Okay, so we will try one by one, nothing wrong. Let us start with the Verilog HDL file, and then I will also show you how to use VHDL, system Verilog, everything. Right, first we will create it, and then we will also see what are the other language template options that are available inside the Quartus Prime Design software. So just select Verilog HDL file, okay, and say okay. The moment you select that, you can see which is the .v extension, and you can see there is a white space where you can type the code. Okay, now let us try the specific principle here. How do we do that one by one? Let us try all the options here. Now, how do we start? We start with the keyword module, and then we'll say adder, and then we'll say input, and A, right? You can say B, and you write here output. Whatever you want, you can try. Simple logic. Right? Now I say assign sum is equal to A XOR B, and you can say carry equal to A and B. Okay? Okay, now what we have done? What is the name of the module that is been written? What are the port connections, right? You need to say, that means what are the ports like input AB, output sum carry. So the inputs and outputs provided. And what is the functionality? Sum is an XR and carry equal to AND. So that is written now. Now we have to save this. What we do is after you develop the code, okay, you have to save it. So first save file and say save as. Right, when you do save as, it shows adder.v. So just save it. That is adder.v. So module adder, input AB, output sub carry, assign sum equal to A XOR B and carry equal to A and B, and module that is provided. So what is the scenario? We have to save that file, that is also saved. Okay, now what is very important is whenever we develop a code, we have to check for any syntax or semantic errors. That is very, very important, because if there are any syntax errors, there is no point in going further, right? So the first step what we are supposed to do is called as analysis and elaboration. So what is the meaning of this step is it is going to analyze your code and ensure that there are no syntax and semantic errors. And it is going to elaborate your code and provides you a gate level schematic. That's what we wanted to see. How do we do this process? When we say in the task tab, right, you have first called as analysis and synthesis. You can expand it. And the moment you expand it, you can see here analysis and elaboration. So as I mentioned earlier, analysis and elaboration is the process which it is going to analyze your code, and also it will elaborate your code to provide the gate level schematic I mentioned. First, let us try that and see what is happening. Then we will come to a conclusion what and all are going to happen inside the design. Okay. Now, first I need to do analysis and elaboration. How do we do that? Just right click and say start. That's all. The moment we do analysis and elaboration, it is going to check the syntax errors, and then it is going to provide you the schematic I mentioned. So you can see that there is a tick on the left hand side, and in the right corner you can see it shows 100%. That means there is no problem. Okay, assuming if there is an error, then what will happen? That also we are interested to see. Okay, just open the code again, and you remove the semicolon from this place, or you remove the colon, whatever you want to remove. Just say save. So assign sum is equal to A XOR B and carry equal to A and B. So there is no right comma. I have missed it. Okay. Now let us rerun the analysis and elaboration stage. The moment you save it, you can see that the analysis and elaboration is grayed out. Again, what you should do is you should start it. Now you can see that it shows Verilog HDL syntax error at line number 7. And it shows that near text C expecting semicolon. There is a colon missing. So it shows that there are 2 errors and 1 warning. So it is easy for the user to go back and identify what is the problem here. Right before the 7th line, you have an issue. So you can see that there is a problem with respect to C. Right? You have to see that the C cannot get processed because there is an issue in the earlier line. So what is the error? We understood that there is a comma missing. We'll insert a comma there. Again, we'll save this design. The moment you save this, again it is grayed out. Right? And now again we can right click and say start. So what is the first step we did? The first step what we performed is called as analysis and elaboration. Okay. Now, whether it will give a schematic, when you say yes, that schematic is called as the RTL schematic, which is a technology independent schematic. It is not going to use any FPGA resources. Okay. Now, how do we check that? When you say go to the tools and go to the netlist viewers and say RTL viewer. Okay. Tools, netlist viewers, RTL viewer. You can see it shows an XOR gate and an AND gate. Assuming if there are any syntax errors, there is no point you will get this schematic, because the moment you compile it, it will show errors. You have to rectify these errors and then only you can enter into this schematic. So what is this step? When you say this step is called as analysis and elaboration step in the Quartus Prime design software. So it checks for syntax and semantic errors and also elaborates your code to provide the RTL schematic. Okay, right. This is one step. Another important thing what we wanted is,
Hello, sir.
yes,
Yes, sir. Based on the code that the schematic is producing is automatically.
correct, you are right. The code gets converted. That means the RTL code what you write, right? Based on this, it is going to provide you the schematic. Since we have written here a sum equal to A XOR B, it is providing an XOR gate. And then we use an AND operator, it is providing the AND gate.
Yes, sir. Whatever
Yes.
we are writing, based on that, we can view in RTL viewer.
You are right. You are right. You are writing a decoder, you are writing an encoder. Any code you write, whatever is written in your code, that will be translated into a gate level schematic. Simple.
Okay, sir.
Right? Okay. Now, what is very important is we are not very much interested directly in the schematic now. Okay, that's fine. Correct. And what is very particularly where we need to concentrate is on the functional simulation. That means we need to know whether the code is working for the intended functionality. Whether the code is working for the intended functionality, when you say, the functionality here means what? It has to produce the correct result, desired result. That means it is an off adder. When I pass 0, 0, 0, 1, 1, 0, and 1, 1, I am interested to see what is the value of sum and carry. That's what is the specific logic of simulation, right? That's what we understood. Now what we have seen is we have written the code and the code is producing the schematic. That is fine. One portion is correct. But in the Quartus flow, if you can recollect, so what we have seen is we also need to do simulation. That is important. Okay, let me just walk you through that and then we will come back. Okay, just give me a minute. Okay. If you can recollect this diagram, you can see that analysis and elaboration. After we do this analysis and elaboration, we need to perform functional simulation. That's what is given here. Okay, what is the meaning of this functional simulation? When you get the idea here is, we are going to develop a test bench which verifies the functionality of the design by passing suitable test vectors. We are going to pass suitable test vectors and then we are going to verify the functionality of the design. That is called as functional simulation here. Okay, how do we do that? That's what we are going to learn in this case. So the code is written and for that code, we have checked what is the schematic. Now the next question what we will have in our mind is, what is the guarantee that the code is working for the specific set of test cases? Desired functionality, how do we verify? When you say, that's what we require simulation. In that case only, our model sim Intel FPGA starter edition is going to help us now. Okay, first we need to create test bench. That's the first scope. Second scope is we need to provide the executable path of model sim to Quartus software so that it can understand that model sim path is specified so it can use model sim for simulation. Right? Because it's a third-party tool which is integrated with the Quartus. We have to be very careful with that. How do we set that path also? I will explain now. Okay, let us first develop the test bench. How do we do that? Go to File, go to New again, and go to again Verilog HDL file and say OK. Adder.v is the design, and I am going to write the test bench for that adder.v. Okay. So how do we do that generally? Module adder underscore tb, which is the test bench. What we all knew is a test bench is a top level module without any inputs and outputs. We won't write any input, we won't write any output. right? And we also knew that it will have data type declaration, module instantiation, procedural block declaration, test case generation, and then display statements. This is the way it will have, right? Whether it is VSTL or Verilog, exactly there will be 5 components in a test bench. Okay. Now in that case, what happens is you have adder.v, and we need to develop the test bench. So what we will do, the inputs will be converted into red. So red A comma B, and the outputs will be converted to wire. So wire sum comma carry we write. So this is called as data type declaration. You can just add a comment so that you will get the idea. Data type declarations. Okay, now what is the next step which we need to learn is called as module instantiation. Module instantiations are exactly same like your VHDL, where we do using positional association as well as named, same. So module instantiation means we need to have the module name, and then we do some instance name, and then you connect it. How do you connect? A is connected to A only, and then B is connected to B only, and sum is connected to sum only, and the carry is connected to carry. Like that we will write. And the third one is called as procedural block declaration. So procedural block means like your process block in VHDL, you have an always an initial block in Verilog. Okay, so we call that as initial, and then you write the test cases. Okay, initial begin, then we should write the test cases. So initial begin. What are the test cases? Initially, I want A and B to be 0. Okay. Then after some time, for example, after 5 time unit, I want the value of A to be changed to 0 and B to 1, just to follow the truth table. And then hash 5, right? You say A equal to 1, and then say B equal to 0. And finally, what you say, I want everything to be 1. So A equal to 1, and then B equal to 1. Doesn't mean that this is the only way to write a test bench. Okay, you have multiple methods. Okay, I'm just giving you a base idea. Now, after writing all the test cases, we should see the output on the screen. That's what we require a display statement. So initial and say $monitor is the statement which you use. Monitor $time. Okay, in VSL we can use assert statements also. So A equal to %B, comma, right? Then B equal to %B. Then you say sum is equal to %B. Then carry equal to %B. A, then B, and sum, then carry. All the things you have written. Now you say end module. Anything you start with module, we should end with the end module. Now you can see data type declaration, module instantiations, procedural block declaration, test case generation, and then display statements we have written. So this is nothing but B stands for binary. $time will tell you this is at 0 time unit, this is at 5, and this is at 10, and this is at 15. We wanted to see at what time unit the values are coming. For that, we require $time. Right? Now we need to save this. Right? So file, save as, and say adder _db dot save this file. Now you can easily understand the moment you save this, right? You can see that analysis and elaboration is again grayed out, because we need to run analysis and elaboration one more time, because you developed a test bench. There may be syntax errors and semantic errors in the test bench also. So you need to again verify it. There are no syntax and semantic errors. Okay. So after that process only we can perform simulation. So what you should do in this case is again go back to analysis and elaboration and say right click and say start. Okay. Now we can see that it shows 100%. That means there is no error in the code as well as in the test bench. Okay. So in the hierarchy tab, if you change that into files, right, you can see the code adder.v as well as adder_tb.v. Both will be there. The code and the test bench, both you can see here. Okay, now what is the next important task which we need to understand is I need to perform simulation. Okay, so to perform simulation, two important steps. One is we have to inform the tool that this is the executable path for model sim. Right, model sim need to be configured. Second important thing is you have to connect your test bench to the DUT. Only then the compiler can understand this is the test bench and this is the DUT. And the test bench need to pass test cases to the DUT, and then we are going to verify the functionality. So the test bench need to be configured. One, you need to configure the model sim. Second one, you need to connect the test bench to the DUT. How do we do both steps one by one? I will show you. The moment you develop a test bench and you verified the syntax and semantic errors, right? What we need to do is you should go to tools. And you have to click here options. So tools, options. In the tools options, you have to select the EDA tool options. When you click the EDA tool options, you can see that model sim altera, and you can see the path is specified. C, Intel FPGA Lite, 18.0, model sim, Win32 ALOEM. So that means this is the directory containing tool executable. And how do we do that? On the right hand side, you can see three dots. You can click that. From here, you can go to the installation directory, go to Intel FPGA Lite 18.0, model sim. Inside that, you select this path. If this is not done, assuming this particular place is blank, you cannot run model sim. It will show error because it does not know where is the executable path. Please ensure that after you install the Quartus Prime Design software, come to tools and options and ensure that this path, executable path, is specified. Okay, where it is available when you say, you can see that here. I will just show that also to you. Go to the installation directory again. Okay, and here you can select 18.0 and then you can see model sim. Right, inside the model sim, you can see here Win32 ALOE. So come to this place. Just select this and say OK. Automatically, this will be configured. All these things are available in the installation folder itself. You don't need to search anywhere. Okay, this is the first step. What is the second step which we are going to do is that you need to connect the test bench to the DUT. How do we do that? Okay, I will explain that also to you. Go to assignments and then we should go to settings, assignments and settings. Okay, here we should go to simulation settings here, EDA tool settings, simulation. If you click here, it shows what is the tool name. It shows none here. Okay. Now what we are going to do is I am going to change this to model sim altera. Okay, what is the tool name? Model sim altera. And I am going to write a test bench and connect that test bench to the DUT. These are the steps we are going to learn in detail later. But now, as a glimpse, you are understanding how simulation is performed, how synthesis is performed, how filter is performed, how are you going to program, everything just like glimpse you are going to see that. So that you will get a detailed picture later. Now what happens is in the compile test bench option, just click that and say test benches. You can see that on the right hand side, test benches. Click that. So it is asking you to create a new test bench. Click that new and write here adder underscore TB. The moment you write here adder underscore TB, right, you can see the file name. So it is asking where is your test bench. Okay, see the three dots here and click that. And here you can see adder underscore tb.v. Select that test bench and say open. Okay, Then you click this add so that the test bench will be added. Now your test bench will be added, which will help you to perform simulation. Now all the dialog boxes you click OK. The final dialog box you click that as apply OK so that it will be applied automatically. So click here OK, OK, and the last one you click apply, then you say OK, so that your test bench is also ready. So what are the two important things? You have to configure the tool, which is your model sim. You have to specify the executable path. Second, you need to connect the test bench to your DUT. Both operations are done. Okay, then how do I simulate? When you say, go to the tools, run simulation tool, and you can see RTL simulation. This is the place where you can perform RTL simulation. So tools, run simulation tool, and say RTL simulation. Click that. And you can see model sim gets popped up here. Right? You can see model sim here. Okay. And on the top, you can see it shows model sim Intel FPGA starter edition. Fine. And then you can see here, when you zoom this, you can see the output also here. So for example, 0, 0 or 0, 1, right? When A is 0 and B is 1, sum is 1 and carry is 0. You can see that here. When A is 1 and B is 0, sum is 1 and carry is 0. And you can also see when A is 1, right, and B is also 1, sum is 0 and carry is 1. You can also see that in the console here. 0 time unit, 5 time unit, 10 time unit, as well as a 15 time unit. All the informations are shown to you for reference here. Right, you can check the functionality using the Model Sim Intel FPGA Starter Edition, which is integrated with the Quartus Prime Design software. So we develop the code, we also verify the functionality. Okay, do you need to have this Model Sim? Yes, you can, nothing wrong. But if you wanted to close only the Model Sim, yes, you can quit it and then you can continue the remaining process with Quartus. Okay, what you can do is, you can just close this. And the moment it asks, are you sure you want to quit? You can say yes. And you can continue the process with the Quartus Prime Design software. So what are the two important steps we did? One, we performed analysis and elaboration of the code. And using the test bench, we verified the functionality of the design, DUT. Right. In these steps, what you can see is, it does not show you how many logic elements it has taken, how many registers it has taken, how many pins it has taken, how many memory bits it has taken, how many DSP resources, multipliers it has taken. Everything it is showing not applicable, not applicable, not applicable. What is the meaning of that is, you have done only the schematic, which is the technology independent. It has not taken any resources which are present in FPGA. In which step it will do that? That step is called as synthesis. Okay, synthesis is the process where it ensures that this is the specific code and it has to choose the specific component which is present inside the FPGA. Now you can go back and understand what I started. You can see there are three important keywords: choose, configure, and connect. Now during this step, right, during the synthesis step only, the tool will find out which are the components. It will choose the component and then it will configure and then connect. Till all these stages it has not, because it is just an analysis and elaboration which is technology independent. Now it has to map it to the corresponding technology. That is the process called as synthesis. Okay. to get a quick glimpse, okay, I have a just small one specific slide which I can show you in detail. Okay, simulation we have seen, but this is something important for you to understand. If you see what is synthesis, this is the idea. It translates the HDL sources into an atom netlist. That means you take the code and the code gets converted in terms of logic cells, flip-flops, RAM, DSP, etc. Now you can understand why I explained about logic cell lookup table, why I explained about registers, why I explained about memory resources, and why I explained about DSP resources, right? Because the code gets converted into what? Logic cells, memory, or DSP resources. So what happens during synthesis in this example we will see, right? And then instead of writing the code, we can also see whether it is possible for us to use the language template. I will show you both scenarios. Okay, let us try that. If the code gets converted into an equivalent gate level schematic, what happens? What resources it is taking inside an FPGA? Let us explore that now. Okay, that is the synthesis process. What is synthesis? When you say it translates the HDL source into an atom netlist, which is a gate level netlist, which is a schematic. But at this case, since there is no gate inside it, it is going to take in terms of lookup tables, flip-flops, RAM, DSP, etc. For this code, what resource it takes, we will see. And I will take one memory code and show you another example, and one memory or multiplier code and show you how it takes DSP. All the three, let us do that one by one. So for this example, it is going to take only lookup tables, logic cells. But for the memory example, it is going to take the on-chip memory which is present inside the FPGA. And for multiplier code, it has to take the DSP resource which is present inside the FPGA. Okay, how it happens, let us explore that right now. Now come back. Any questions you have before I perform synthesis?
Sir?
Yes.
Yes, sir. For example, if we write the code or requirement based on memory and the DSP, that but some other block also present in FPGA, no, sir. Based on the code, it take memory and the DSP means, and other blocks are what will happen?
Correct. So in our code, for example, it can take lookup tables also, right? What I'm telling is it can take lookup table, memory, DSP, everything, and all the things also, right? In one code, you can take 500 ALMs, and it can take 10 memory blocks. It can also take 2 DSPs. All are possible with a single code also. But now, since our code is a very small code, there is no point in taking memory because it is a gate. We only know, right? It's a logic gate code. And another example, what I am going to show is it is going to use only memory. And third code I am going to show you, it takes only DSP. But tomorrow when we have a big code, which can take all the resources also. But I wanted to show you specifically for this code, this resource, for this code, this resource, then you will get an idea that tomorrow if I show a big code to you, then you will easily understand that for this portion, it will take lookup table. For this code, it will take memory. For this portion, it will take DSP. Is that clear?
Yes, sir.
Right. So this is just to split and understand. But tomorrow when we have a huge code, I will show that also to you, which will automatically take all the resources. But then at that time, it is very tough for us to analyze because it is a big code for us. But since we are dividing it and understanding that today, like, okay, for this code, it will take this resource. And when we try to analyze a big code, it is very easy for us to grasp things. Is that clear?
Yes, sir.
Okay. Yeah, thank you. So let me just show that to you right now what happens. Okay. How do we do synthesis? Let us first try that. We'll stop with synthesis today. No need to confuse much. Okay. But I want to show that what resources it takes. That is very important for everyone to understand because that is the kind of takeaway today. Now, if I do synthesis, that means what happens? Let us explore it here. There is a step called analysis and synthesis. Okay. Just click that and say start. Now it shows. This is the step I want everyone to understand. It shows two logic elements. Earlier it showed everything what not applicable, not applicable, because it has not used any resources from the FPGA. But in this step, when we do synthesis, it is showing that it has taken two logic elements and registers 0 because it's a pure combo logic. Number of pins 4 because A, B sum carry. No memory because it's a simple logic gate code. No multiplier because it is a simple logic gate code. So what I wanted is, I want to show you a code which should use memory, and I also want you to get into a code which should use DSP resources, so that you will come to know that for this code it will definitely use memory, for this code it will definitely use DSP resources. That's the idea. Definitely for this code it will take logic elements, we are aware, because it is just a simple gate level logic code. Okay, now let us see what happens inside this. How do we know that what is the schematic, right? First we will see the schematic, and then I will also show you how to analyze the report. Go to tools, go to the netlist weavers, go to the second one, technology map weaver, post mapping. Post mapping means after synthesis. After performing synthesis, if you are seeing the schematic, that is called as post mapping. After placement and routing, if you are seeing the schematic, that is called as post fitting. That we will worry about it later. Now what we wanted is, if the code gets synthesized, what is the kind of schematic will it give? That's what we wanted to know. Earlier we have seen like a gate, right? But there is no gate concept available inside the FPGA. We have a concept of lookup table. So what resource it takes, let us see that. Just click that. And you can see data A, data B, and then combo out. Data C, data D, combo out. Something like that it shows. But it does not show that it is a gate. Okay, it shows like a lookup table, a logic gate, logic cell. But I want to know what is inside this logic gate, right? Inside the logic cell, what is available is the interest for us. Okay, double click that. You cannot go inside because it is like a logic cell. But then we can see the properties. What is this? Is the interest for us now. So what you can do is right click and go to properties. If you go to properties, you can see it is nothing but an AND gate. So instead of an AND gate, it shows like a logic cell, because that is the resource which is present inside the FPGA. Now for this, I wanted to know what is the truth table. Right, what you can do is just click here, truth table. You can see that 0, 0, 0, 0, 1, 0, 1, 0, 0, then 1, 1, 1, because it is a 2-input lookup table. For 0, 0, what is the output? For 0, 1, what is the output? For 1, 0, what is the output? And for 1, 1, what is the output it is showing. Not only that, you can click the equation from here, which shows that the output C is nothing but the AND operation of A and B. It shows data A and data B, which is the AND operation of A and B. That's what it is, an AND gate. But this AND gate cannot be seen directly here, because it is going to use only the logic cells, the lookup tables which are present inside the FPGA. Please keep that in mind. The similar case, if you wanted to see here for this logic cell, what we can do is right click and again go to properties. When you go to properties, you can see it is an XOR gate. Right? You can see A, that is data C and data D, and then it shows the combo. Now, if you click the equation, it is nothing but the dollar. This dollar is nothing but your XOR symbol. And if you need to see the truth table, right, you can see that for 0, 0, it is 0. For 0, 1, it is 1. And for 1, 0, 1. And for 1, 1, this is 0. This is the truth table of the lookup table. That's what we call that as LUT, which is the lookup table. Now, this is the way how you can see the synthesized schematic. Okay, not only this, here you can see it shows total number of logic elements, right? But we wanted to know how many input lookup table it has taken, whether it is 2 input lookup table or 3 input lookup table or 4 input lookup table, like that, right? And this device, the Max 10 device, has a 4 input lookup table. That's the maximum here. So which lookup table means we are very sure it should take only 2 input lookup table, because A, B, and then you have sum. Only 2 inputs are there. So, but I wanted to get that information from the tool. We wanted to analyze the report. How that can happen when you say expand here, analysis and synthesis, and you can click here resource usage summary. If you click that, on the right hand side you can see estimated total logic elements 2. And it shows that 4 input functions 0, 3 input functions 0, 2 input functions 2. So this is the way an FPGA design engineer will understand what resources are used, right, from our code. And you can also see what resources of FPGA are used by our RTL. Now we are very sure that it is not going to use a 4 input function, because our code has input AB, that's all. So definitely it is going to use only 2 input function. So that's what it shows, that 4 input functions 0, 3 input functions 0, and 2 input functions 2. Right? So this is one way of analyzing. When we go further, it shows that, or it is using any memory. When you say, you can see that embedded multiplier 9-bit element 0. It is not using any multiplier. It is not using any memory resources. Everything is 0. Why it is showing everything 0? Because this code is a simple combinational logic, which is not going to use any memory resources at all, not required. So this is the way how you can analyze. So what is this process? This process is called synthesis. So synthesis is the process in which the code is translated into equivalent gate level schematic. In our case, it is a technology dependent schematic. That means it is going to use the resources which are present inside the FPGA. The schematic what we are going to see is exactly the same what is present inside the FPGA. But that was not the case in the earlier one. That is called as RTL schematic, which is called as RTL Weaver. That is the schematic which will use the basic elements, right? It is not going to use the resources present inside the FPGA. So what we have seen now, a simple gate code we have written, so that is going to use the lookup table, basic resource. What is the next resource we want is called memory. And what is the third resource we wanted to see is called DSP, which is a multiplier. Okay, one by one, I will explain that also to you. Okay, you have done with this project today. You don't want to continue fitter, you don't want to implement nothing, right? You want to close it. When you say, it is very easy to close the project, and you wanted to open it tomorrow or day after tomorrow or later, you can definitely open it. Okay, and it is available in the same way where you closed it, and then you can continue from there. How do we close this project? When you say, go to File and say Close Project. The moment you click Close Project, you can see that this is the project which we closed. That comes on the top, which is called as the recent project. And the extension of that project will be QPF, which stands for Quartus Project File. Any Quartus project file which we closed, right, will come as a recent project today. But if I go on creating 5 projects and then close it, then all these other projects will go, and then you can have at a time only 4 projects that listed. The extra projects, you have to go to open project and then you should take it. That is the only way to get the already existing project. Okay, let me create the second example, and I will create the third example. And for the second example, we can come up with memory, and the third example, we can come up with the multiplier. And then later when we go through the different set of complex designs, you will have multiple resources in the same design. That means when we create a system level design, where we will have all the resources that are used inside the FPGA. Let us try this now. How do we start again? Remember, whenever you need to create a new project, always you should click the new project wizard. Don't forget that. Then come to next, and it shows example 1 design. I will change this to example 2 design. And what is the name of the memory? I say mem. One important concept I am going to show you is we are not going to write the memory code. Instead of writing the memory code, we are going to use the language template that is available inside the Quartus Prime Design software. How to use it, I will explain that in detail now in this specific example. So click here mem, say next, say yes, empty project, say next, add files, nothing to add, say next, come to this place, remember select max 10, and in the name filter type 10M50 BAF 484 C7G. Select the device, say next, and then finish. Okay. Now exactly like the similar version, just go to File, New, Verilog HDL. Same. But now we are not going to start typing the code, module, memory, like that we are not going to. Instead, what is the option available in the Quartus when you say, we have a language template that is available, which will help you to insert the template for the codes, which we are not very much aware or not comfortable at the junction, right? You can try it later and customize it, but at this junction, you are not aware of the coding style. We can directly take it from the Quartus. So click here, insert template. Click that. Once the dialog box gets opened here, you can see it shows Quartus Prime Tickle, Timing Analyzer, System Verilog, Tickle, Verilog HDL, etc. You can select Verilog HDL here. Expand that. Go to full designs. Because I don't want to type partial, right? So full designs you take. Expand RAM and ROM and click single port RAM. I wanted to get the Verilog code of a single port RAM. So just to say insert and say close. You can see that the entire Verilog code of the memory is available here. What is the only change you should do is the name of the memory is shown as single port RAM, but while creating the project, we gave our name as mem. Just only that change you do. All other things, let it be as it is. Okay. Now you have the entire Verilog code. The same is available for VHDL. The same is available for System Verilog also. No worry. So you can take that module, and what you should do is save it as mem.v. So file, save as, and say mem.v, and then save. Okay, sorry, just I'll take a cup of water. Now what we have done is, we have developed the logic here, which we have saved this file as mem.v. Now what we are going to do right now is we perform analysis and elaboration first. Okay, let us do that. How do we do that? Expand this analysis and synthesis. Go to analysis and elaboration. This is one way. If you want a shortcut, okay, that is available here. So this is called as analysis and elaboration. You can see here, start analysis and elaboration. The shortcut key is Control K. You can type that. Otherwise, you can do it from here. Anything is fine. Okay. So if you're aware with only about this, you can try this here. Analysis and elaboration. We can learn everything later. At this junction, let us try the first method. Okay. Now, when we do analysis and elaboration, go to tools, go to netlist viewers, go to RTL viewer. You can see it shows the RAM memory. It shows flip-flop, register and memory. Right? What is the data? 8-bit, Q output 8-bit, and then write enable 2 power 6. Right? That all these informations are shown now. Address lines, everything. Now, if you see the resource report, it shows everything not applicable, not applicable. That means it is not using any resources which are present inside the FPGA. Which step is going to do that when you say when we perform synthesis? Okay, well then why this step when you say if the code is not providing the correct hardware, what we wanted, there is no point in continuing the other step, right? Because sometimes the tool will provide you something, some resources which we feel that may not be the proper one. Another way is after performing synthesis, right? We can perform some optimization technique. We can give some attributes. All those things are available, right? And another important thing with RTL schematic is we can get a clear picture that, okay, what is the kind of replica of the resources which we are going to get after synthesis. Okay, let us try the synthesis step here. How do we do that? Go to analysis and synthesis step, right click and say start. Now you would have seen there is a specific difference between the earlier code and this. In the earlier code, total number of logic elements it showed 2, but memory resources and DSP it showed 0. But now you can see that total number of logic elements is 0, registers is 0, but total number of memory bits it shows 512. So which is the width and depth? Right or not? So that's the process now. So we need to know that how it is generating the logic. Okay, so you can see 64 into 8. It shows that 512. Scenario logically, you can check that. Now, what is very important now is it shows total number of memory bits 512. Then what is the resource it is taking? That's what we wanted to see. Okay. Expand this analysis and synthesis. Go to the resource usage summary. And here you can see total number of memory bits it shows 512. So what is the resource it takes that we can see? We can also see that in the schematic. Tools, netlist viewers, and say technology map viewer post mapping, which shows your memory. You can see that. Just a minute. RAM block. Okay, so the way the code is written, the tool converts that into an equivalent gate level schematic. Right, you wanted to modify the parameters as per your customization, that can be definitely done. Right, now you can relate what is the way the code is written. For that code, what resources are available inside the FPGA, that resource it will take. Now the question is, do you have only one memory? When you say no, there are multiple memory resources that are available. And for our code, the tool has taken only 512 bits. Okay, and what is the capacity of the memory that is available in each and every device? That's what we need to enter into each and every family. So Maxton has what device? What kind of memory? How many memory blocks are available? That's what is the kind of discussion we are going to do in the later classes. Based on that, we will come to know that how do we choose a specific FPGA. This specific FPGA is fine because I'm going to write a code which will take more number of memory blocks. Whether those many memory blocks are available inside that FPGA. If the memory blocks are full, then what is the kind of resource it will take? All those questions we can get answers when we get into the detail. Okay, so one side what we have seen is the lookup table. Another side what we have seen is the memory resources. The third important resource which we need to discuss is called as the DSP resource, which is called as the multiplier and an accumulator resource. Okay, let us try that. And we can also see a code which brings everything. That means it has a lookup table, it has registers, it has memory, something like that also we can try. So how do we close this project again? Say file and go to close project. So the basic lookup table example over, and the basic memory resources over. How do we get the DSP resources, which is called as a dedicated multiplier and an accumulator unit? How do we do that? Again, go back to new project result, say next, and change this to example 3 design, and call this as mult, because a simple multiplier example. And next, create it, say empty project, no need to add any files, go to max 10 and use the filter 10M15 BAF484 C70. Select a device, say next, and then finish. Exactly same like the earlier example. Go to file and say new, click Verilog HDL file and say OK. But the difference now is go to language template, insert template, expand Verilog. In the full designs, expand arithmetic. Okay, in the arithmetic, you expand multipliers. And you can take any design here. Okay, unsigned multiply with the input and output like that. Or else you can also directly go to DSP features and take any DSP multiplier also. Sum of 4 numbers, sum of 3 numbers, whichever you want. Okay, for example, let us take one simple logic here. That can also be possible. Okay, but at this junction, let us start with a small multiplier so that you will come to know that while writing the code, what device it takes. So take multiplier for complex numbers. Say insert and then close. Change this multiplier for complex numbers to just mult, because that is the name we provided. Okay, we are not very sure that whether it is going to use DSP resource itself, right? It can choose some lookup tables and flip-flops itself to generate a multiplier, right? That is the kind of challenge we get, because sometimes the tool will try to compromise between those resources, right? That's what we have different attributes to get it, that we will learn in detail during the HDL coding techniques session. Okay, now we can see file, save as, and say mult.c. So you have a Verilog code of a multiplier, which is taken from the insertion template option. Just continue with the analysis and elaboration. Okay, now what we can do is go to tools, go to the netlist viewers, and then go to RTL. You can see multipliers are used, mult, adder, and then register. So what you can imagine is this multiplier and accumulator block can be using a DSP resource, or this multiplier and accumulator can be replaced with a lookup table and a register. Multiple number of ALMs are added together in order to accomplish this task. And we can ensure that this is completely using only the ALM blocks other than DSP resource, also possible. But what it is generating, let us identify. Okay, so close this. And you can continue with the synthesis option. So click here, analysis and synthesis, and say start. Okay, now you can come to know that It uses 72 logic elements, 72 registers, and 8 multipliers. You can see that 8 embedded multiplier 9-bit elements. If you expand the synthesis report and you click here resource usage summary, it shows here estimated total logic elements 72. In that, it is not using any 4 input functions, 0, but 3 input functions 70. It is using 73 input lookup table and two input lookup table. Okay, and then you can also see that it uses 72 registers, and then it also uses 8 multipliers. So it is using DSP resources, it is using dedicated logic registers, it also uses the lookup table. Everything we can get from the resource usage summary, which is provided by the tool. Okay, we wanted to see the schematic. Go to tools, go to the netlist viewers, and then go to technology map viewer post map. Now you can see that. Now you can understand which is the critical path, right? Now it starts from here, right? You can see that it starts, and you can see that how complex is this, right? See, all the resources are here, and then you can see the path there. This is the output. You can see what is the longest path. Now, how this design will meet timing, that is again a challenge for the design engineer here. Okay, now if you click this plus, it will expand this as a multiplier block, because this is a DSP mult. In the earlier example, it doesn't show that because you don't require. But it is very clear that this is a multiplier code, it has to use that. So now you can understand, if you have a code which uses lookup tables, which uses memory, which uses DSP resources, etc., then how complex will be our code, and how are we going to perform synthesis fitter without any problems, and then how are we going to achieve the timing closure? Easily we can understand it is not easy, right? With the small design itself, a small design, a multiplier design itself, you can understand how complex is that. But when the design becomes complex, it is very critical for us to do. That's what you will have different steps and different optimization logics and different techniques that could be adopted in order to accomplish that timing closure logic. So now you can understand what is the resource. Now, from this, what is the learning when you say, on seeing the code itself, the design engineer can say which resource of an FPGA can be taken for this code. That's our experience. So on seeing the code itself, you can see this is a multiplier code. It will take these many DSP resources. This block of this code will take this much memory. This block of this code will take this much lookup tables. We can tell that. So that itself will give a clear picture that what is the resource and how do we correlate with that hardware. So our success is on seeing the code, we should tell what is the resource. Then optimization becomes easier, right? That's the kind of logic. Now with these examples, you can see that I know that there are lookup table resources inside my code, but what resources it is used by my code, you can see that now. Similarly for the memory resources, similarly for the DSP resource, which is a dedicated multiplier, everything I have shown. Right? So now what is very important here? We should be familiar with any one of the HDLs, either Verilog or VHDL or system Verilog. Because when we are familiar with any one of the language, what is happening, we really know how to write the code, then we will save a lot of time, because when the code gets converted into an equivalent gate level schematic, we will come to know what are the different optimization methods. Assuming that we are not following the proper HDL coding techniques and then we are writing the code as ever, whatever we like, then optimizing that for FPGA becomes very tough. Okay, so that's what we have to be very, very careful. Sometimes we may develop a code, but that code may not get optimized because we would have followed some poor coding practices and developed the code. It may work for functionality. It may be absolutely fine with respect to functionality, but it may not appropriately fit into the FPGA. It will not use the effective resources what we wanted. Right? That's what this course will help you. Where which code will give you what kind of resources and what are the best HDL coding practices that need to be taken into account. Okay, so to get a good feeling of that, there are two documents. I can just show that to you whenever you are free. Please go through that. One is the HDL coding practices. Okay. So when the moment you enter into this, it will automatically take you to a link called recommended HDL coding styles. So I request everyone to go through that because even we have a fair knowledge on all the HDLs, but sometimes what is very important for us is how do we optimize that code for the FPGA. That is very, very important for us. That's what we should go through the recommended design practices. Here, what I showed was when I write a code, I am very sure that that code will take a multiplier. But how do I know that any code will take a multiplier, right? That means whether this particular function will take a multiplier. So you can see that inferring multipliers. On which way I can infer multipliers. You can see that the VHDL code is given, the Verilog code is given. You can see the VHDL code as well as you can see the Verilog code. So you can just copy this code and paste that and see what kind of multiplier. You can see it shows the directly copy code. You can just click here, copy, and then directly paste that into the Quartus Prime design software. So I recommend everyone to do this in this week so that you will get an idea. This is not only for VHDL, it is available for Verilog as well as for system Verilog, right? You can copy the code and you can paste it and see what is happening. This is for signed multiplier. So that you don't need to create anything from scratch. You will be getting an idea for this kind of code, what is the kind of resources you will be getting. That's the basic logic. Mapping your code to the corresponding hardware, what is present inside the FPGA. This is the first thing. This is the basic resource. The second important thing which you need to go through is called inferring memory functions in the code. The moment you develop a code, how do you know that this code uses a kind of memory templates which are available? There are so many available for VHDL. There are so many available for Verilog also. There are so many available for system Verilog. At this junction, just leave system Verilog. Try with Verilog and VHDL. So you can just click here, inferring RAM functions from HDL code. Inferring ROM functions from HDL code. Inferring shift registers from HDL code. And inferring FIFOs in HDL code. First in, first out. It can be a synchronous FIFO or an asynchronous FIFO or a single clock or a dual port FIFO. Yeah, dual clock FIFO, which is an asynchronous FIFO. How do I do that? Everything is explained here. So just go through that. This is the second thing which you can go through. The third one is called as the recommended design practices. This is one which every design engineer should take advantage of. Because whenever we develop a code for a corresponding FPGA application, most of our time we are getting wasted with our design practices, because once we are thorough that are aware of what need to be written, then we don't need to worry about what happens inside FPGA, because we are very much sure that when the code gets converted into a get level schematic, what resource it will take. Okay, where are the resources? How do we get more information when you say? That comes here. Synchronous FPGA design practices, HDL design guidelines, implementing embedded RAM, and there are multiple options. Okay, just go through what is possible from your side, because that will definitely help you that when we have the code with us, then that code will realize what kind of hardware. That is very, very important for a logic designer. If that is known, then applying timing constraints, achieving timing closure, and then generating the SRAM object file, implementing onto the FPGA, performing any other task later, that debugging or anything, that would be easier. And HDL design guidelines is the chapter which will help you to get into logic. For example, optimizing the combinational logic. You are writing a code which is going to use only lookup table and ALM. No other resource it is going to take. Then in that case, where and how we should be careful. So just first question is avoid combinational loops. So while writing the code, please be very careful in removing the combinational loops. This is what we are going to learn in detail, so that when the code is perfect, when the code has the best HDL coding practices, and we are aware of the architecture, number one, and we are aware of what is the best code to be written, then what else is required? Nothing is required. We know the internal structure of FPGA. We know what are the resources which are present inside it. And we also know that what is the best coding practices. Then we will spend only less time, right? Because all the things tool will take care. But when we are not aware of that, then we have to spend a lot of time here, because all other things will be taken care by the tool later, right? In the first initial stages, we spend time, then all other steps will be taken care by the tool automatically. This is one small document which you can definitely look into. You can just type recommended coding practices with Quartus. You can download this document. On the right hand side, you can see download. This will come as a PDF. You can just go through two pages daily to get an idea of what is happening. Also, you can directly copy the Verilog or the VHDL code, right, from the soft copy, and paste that into Quartus Prime Design software. Just click synthesis and see what hardware it provides. So that multiple code will provide you different sets of hardware that will give you a proper logic. How do we proceed? Right? These are the scenarios which we look into. So what is the key takeaway? If you see, we have seen what are the resources, which is like the adaptive logic modules. And then you have seen memory resources and DSP. For all of them, I showed you one example. How to write a code for a lookup table, that we are very much aware, one gate code. How do we write a memory code so that I should get memory resources? That also I showed you. How to write a multiplier code so that I should get the DSP resources? For that also I showed you. And the fourth one is the very important takeaway, that what are the recommended HDL coding practices provided by Intel, so that it is easy for us to develop the correct logic. So the good advantage is if you can get the correct code, then all other processes are very easier. If you have a wrong code, then we cannot proceed further, right? We cannot cross synthesis itself. Then how are we going to perform timing analysis, timing closure, and all those operations, right? They are very tough. That's a scenario. Now what we can do is like, this is the step which I mentioned, right? So you remember this. During the synthesis process, it is very clear that the code what you take will be converted into a gate level schematic. It can be in terms of logic cells, flip-flops, IOs, RAM, DSP, etc. And one more thing which you need to know is about simulation, that since I have done that, I will just show you only one flowchart for you to understand. Whenever we do simulation, as I mentioned, right, we create a project, we compile the design, we create the script. That means you develop the simulation logic. You simulate the design, you check the test bench. But sometimes what will happen when you simulate and you see the output in the console, we may not be happy with the test cases because we passed correctly or the code is not working functionally correct. There is a functional problem, right? You'll be expecting that it works as an encoder, but when you see the output, it works like a decoder. Then what will you do is like you cannot say yes and then directly go to synthesis, right? In that case, we have to fix the design. Again, you need to go back and compile it in the Quartus. Then only we can go to the next step. Okay. And two more important slides which I need to show you, right, is this, right? One, you have a test bench. Okay. What you need to do is you can have the Quartus, which is using the model sim. Okay. What is important here is the first step is this. I explained that, but still I wanted to show that in the slide. Go to tools, go to options, and go to EDA tool options. And in that, ensure that the model sim Altera you have selected and provide the executable path. This is the first step which we need to do. What is the second step? Is go to assignments, go to settings, EDA tool settings, go to simulation. In that, you should select model sim Altera. Compile test bench, you should click new. Then you are going to create a new test bench and then run. How do we run? Run simulation tool, RTL simulation. Then you can see the output in the transcript window. So all these steps are shown to you, right? Because this is like a basic class for you so that things are touched upon so that we can get into the details of each and every section in the coming classes. Do you have any doubts? Any questions you have? Please let me know. I feel you would have got some overall picture of what is the kind of logic you are going to get. Any feedback or anything is welcome, no problem.
Sir, is the coding is same in all in Intel and Xilinx in lattice everything, or in coding also there will be a difference? The
There may
basic
be,
code,
yeah, so the basic HDL coding style may not be much difference, but if you are inferring a specific component, for example, I wanted to take an 18x18 multiplier. The same 18x18 multiplier may not be there in Xilinx or Lattice, right? Because they may have a different set of DSP block, right? So in that case, your code may take 2 DSP blocks. In that case, there they may take 4 DSP blocks. That we cannot say. What is the kind of resource that is present inside that? It will try to infer that component. Okay, only when you are trying to see the resources which are present in that specific FPGA, if you want to take that component, there only these best coding practices will help you. In all other cases, like what generally the HDL coding practices are following, the same is sufficient. No much changes.
okay, sir. Thank you.
Hello.
Yes.
Sir, if you don't mind, I joined a little late. If you don't mind, can you explain that how to installation that software, the tools?
No problem.
in lab- in
I can
this-
definitely do that. No issues. I can do that. So you can go to FPGA software download center. Okay. In the download center, the moment you get this page, you have to select the Intel Quartus Prime Lite Edition. For example, if you click this will show me 3 things. One is Pro, Standard, Lite. In our class, we are going to use only the Lite Edition. Click that. And directly go to 18.0 or 18.1. for Windows. Select that. And from there, what you can do is you have a specific device file, which is 5.8 GB. Download that tar file, which includes model sim also. Okay. Just to put that in a directory and then run the setup.batch file. That's all.
Okay, sir. Thank you.
Right. So if you have any questions, please let me know in the later classes also. It's like an initial class. So if you can just at least have the tool ready, you will have some idea of how to use it and then get a basic feeling of it.
Hello, sir.
Yes.
Yes, sir. You mentioned that recommended HDL coding style. What you suggested, VHDL, Verilog, or System Verilog?
Right. So this HDL coding practices are common. Like for example, it is not related to any HDL. All are common, like Verilog, VHDL. Because if you see the guide also, it has the template for both Verilog as well as for VHDL. But
Yes,
sometimes what will happen is there are some constructs in the language which may not be useful for synthesis, right? So when we are doing system Verilog, we have to be very careful that what constructs are useful for generating hardware and what constructs are not useful for generating hardware, which is useful for test bench. So here in these coding practices, for the specific language construct, which is going to give hardware, which is not going to give, only that information we should know.
Okay.
Right? But the specific, for example, if you take, I want to write adder, in all the three languages, adder will give the same kind of hardware, no difference. But when I am trying to write the same adder using structures in System Verilog, then I will have a difference because structure is a new concept and it is introduced only in System Verilog. What kind of adder it will give, that confusion will come. So these kind of guides will help you to have a specific feature in that language, what kind of hardware it will be related to.
So I thought maybe advantage and disadvantage are present in VHDL and Verilog. Sir?
We cannot compare any HDL like that. Okay, for example, VHDL and Verilog, both are HDLs, right? Both have the characteristics of simulation, synthesis, and documentation. Okay. For example, if your project has started with VHDL and then you wanted to develop only in VHDL, nothing wrong. And then there are now mixed language simulators available. So there is no specific comparison between any of the HDLs. Both are good.
Okay, sir.
Yeah. It all boils down to what is the kind of project we work on and what is our requirement. Are there any other questions? If not, it is over to the IIT organizer.
Hello. Is it the same timing on the coming week, sir?
Probably yes, I feel. So Dinesh can add more details with that.
Okay.
So I hope he is there or not there. I'm not very sure. I have just put a message in the chat also.
Okay, sir.
Yeah, please. Okay, then thank you then. If there are any other communication, please check with Dinesh and then we'll meet next week.
Okay, sir. Fine. Thank you so much, sir.
Thank you.
Yeah. Bye.
Thank you.
Yeah.
Welcome.
Bye.
Bye. Bye.
Bye, sir.
हेलो
हेलो, यस
हाँ सर, क्या इसका रिकॉर्डिंग मिल सकता है क्या?
That information you should get from Dinesh only. That's what I'm trying to reach him. I hope he's muted.
Okay, sir.
Fine,
Thank you.
Thank you. Yeah.